Hello, and welcome to 3 hours of science for sleep. I'm glad you're here, whether it's night, morning, or somewhere in between. This is your time to unwind, breathe, and drift into rest. If this video helps you relax, feel free to like or subscribe. It truly helps me keep making these calm, quiet journeys for curious minds. Tonight's topic is a gentle one, but strange in a beautiful way. Time doesn't pass the same everywhere. On top of a mountain, it moves just a little faster than it does in the valley below. It's not a trick, it's physics. For the next few hours, we'll explore why, slowly, softly, from Einstein's thoughts, to satellites, to the tick of a clock, all explained in a way that helps you drift into sleep. So, get cozy, and let's begin. Imagine standing on the top of a mountain. Not one of those sharp, snow-covered peaks, but something softer, rounded slopes, patches of wild grass, cool, quiet air. The sky feels just a little closer here. The world below, a little farther away, and time just slightly different. You wouldn't notice it, of course. Not by feeling it. Not with your eyes. But something strange is happening up here. If you brought a perfectly precise clock with you, the kind used by scientists, and placed another identical clock at the bottom of the mountain, the two clocks would slowly drift apart. The one in the valley would tick just a little bit slower. This gentle difference isn't magic, it's gravity, and it's one of the quietest truths in modern physics. For most of human history, we thought of time as fixed, steady, dependable. A river that flows in only one direction. Seconds become minutes, and minutes roll into hours, no matter where you are. But it turns out, time doesn't flow evenly everywhere. It stretches, it bends, and up on a mountain, it flows just a little more freely. This idea might seem strange, but it has been tested, measured, proven, and repeated in quiet laboratories and high places around the world. And, to understand why, we'll start not with clocks, but with a thought. A long time ago, in the early 1900s, a quiet man named Albert Einstein sat in a patent office in Switzerland. Outside, trams rolled by. Inside, he imagined what it would feel like to ride alongside a beam of light. What would you see? What would you feel? This simple question led to one of the most profound shifts in our understanding of reality. Einstein began to see time not as a constant, but as something woven together with space itself, a fabric, soft and curved, shaped by mass and energy. The more mass something has, like a planet or a star, the more it bends the space and time around it. This bending is what we call gravity. Picture a large rubber sheet, stretched tight. Place a heavy ball in the center, and the sheet dips. Now roll a marble nearby, and it curves toward the dip. That curve isn't caused by a pull. It's the marble following the shape of space. This, Einstein said, is how gravity works. And because space and time are connected, bending one bends the other. In places where gravity is strong, time flows a bit slower, and in places where gravity is weak, like the top of a mountain, time flows a bit faster. This phenomenon has a name: gravitational time dilation. It sounds complex, but the idea is simple. Gravity warps time, and when you move away from the source of that gravity, like by climbing a mountain, you're moving into a place where time is slightly less bent. Scientists have tested this with extraordinary precision. They've taken two atomic clocks, one left on the ground, the other flown in an airplane. And when compared, the one that spent time in the sky ran just a little bit faster. The difference is tiny, nanoseconds, but it's real. So real, in fact, that our modern world depends on it. Global positioning systems, GPS, rely on satellites orbiting high above Earth. Up there, gravity is weaker, and if we didn't account for the fact that time flows faster on those satellites, our GPS systems would fail within hours. Your phone would tell you that you're miles from where you actually are. Einstein's equations keep your directions accurate every day, and they all began with a quiet thought about light, and time, and space. Now let's return to the mountain. It's quiet here. Maybe there's a breeze. Maybe the sun is just starting to dip behind the hills. Your body feels still. Your breathing is slow, and all around you, the air holds a secret. You are aging just a little bit faster than someone in the valley below. Not enough to notice, not enough to feel, but enough that physics can measure it. Enough that satellites depend on it. And enough to remind us that the universe is always doing something quietly astonishing. In fact, the effect is happening inside your own body. Your head is farther from Earth's center than your feet, and so, in theory, your face is aging just a fraction of a second faster than your toes. Imagine that, your own body, experiencing two different versions of time at once. This gentle discrepancy doesn't hurt us. It doesn't affect your health, but it's a soft reminder that time is not a uniform blanket. It ripples, it bends, and it flows differently depending on where you stand. And the higher you go, the freer it flows. So what does this mean for us? Here on Earth, does it change the way we live? In most ways, no. But in subtle ways, in the quiet ticking of clocks and the whisper of satellites, it changes everything. The gravity isn't just pulling you toward the Earth. It's also gently stretching your time, every heartbeat, every second, every breath, all shaped by the mass of the planet beneath your feet. And when you climb higher, you step ever so slightly outside of that pull. You rise not just above the land, but above a thicker moment of time, and maybe that's why mountaintops feel the way they do. Not just vast, but unhurried. Not just distant, but timeless. Of course, the difference is too small to feel, but maybe, in your imagination, you can sense, maybe you feel just a little lighter, a little freer, a little closer to the stars. Einstein's theories don't just live in textbooks, they live in the slow drift of time, on a mountain, in the curve of space, beneath your pillow, in the ticking of a satellite, 12,000 miles overhead. And tonight, they live here too, in the calm rhythm of this story, in the soft breath you just took, in the gentle way the world continues, quietly, astonishingly, differently than we once believed. And so as we close this chapter, you can rest, knowing that even now, as you lie still, your time is moving in ways you may never feel, but that science knows are real. And somewhere, high above the Earth, on a quiet mountain slope, a clock is ticking, just a little bit faster, just like Einstein said it would. Every day, you carry a quiet miracle in your pocket, or maybe it rests beside you on the nightstand, glowing softly. Your phone, a piece of technology that connects you to the world, to friends, to maps, to messages, but inside it, tucked beneath the screen, and the apps, and the photos, is something extraordinary. A connection to space, a constant, silent conversation with the sky, and in that conversation is a secret about time. It begins with the Global Positioning System, or GPS. You've likely used it without thinking. You open a map, a blue dot appears, and somehow it knows exactly where you are. But how does it know? The answer begins far above your head, about 12,000 miles up. To be exact, orbiting Earth are dozens of satellites. Each one moves in a precise path, circling the planet twice every day, and each one carries something very special. A clock, not just any clock. A perfectly precise atomic clock, one that measures time so accurately, it would lose only about 1 second every 100 million years. These satellites are constantly broadcasting signals, and each signal contains two important pieces of information: the satellite's position and the exact time the signal was sent. Your phone listens. It receives those signals from multiple satellites at once, and by comparing the time the signals were sent with the time they were received, it calculates how far away each satellite is. From that, it triangulates your location. It's like a game of cosmic hide-and-seek, but the hiding spots are moving at 8,700 miles per hour, and the seekers are measuring billionths of a second. For this to work, the clocks on the satellites have to be perfect, or rather, they have to be predictable. And here's where the sleepy secret comes in, because time flows differently in space. We've already explored this idea together, how gravity and speed affect time, and GPS satellites are affected by both. First, they're far above the Earth, where gravity is weaker. This means time ticks faster for them than it does for us on the ground. But they're also moving very quickly, and motion slows time down. So those two effects are in competition, and yet they don't cancel out. Not exactly. When we do the math, we find that the gravitational effect, the fact that they're farther from Earth, wins out, and the clocks on GPS satellites tick about 38 microseconds faster per day than clocks on the ground. That may not sound like much, but over time, it adds up. A few microseconds might not mean anything to a person, but to a system that measures distances by the speed of light, those tiny discrepancies can cause errors of several miles. Imagine trying to find a restaurant and ending up in the next town. So engineers do something clever. They pre-correct the clocks on the satellites. They slow them down just enough so that once they're in orbit and affected by the weaker gravity, they'll tick at the exact right speed for Earth-based receivers. It's like sending a traveler ahead of you and packing them the right shoes to match the terrain. Every moment, your phone is listening to this delicate ballet, signals from space, timing adjustments. Einstein's equations whispered through the air, all so that your map can tell you where the coffee shop is. It's strange to think that relativity, an idea that once seemed abstract and far away, is now part of your daily life. Quietly, constantly, elegantly. Einstein probably never imagined that his theories would one day be built into a device people use to find brunch. But that's the beauty of science. Even its sleepiest secrets can become everyday magic. And the more we understand about those satellites, the more we see just how carefully the universe works. Because every part of the GPS system depends on one simple truth: time is not absolute. It bends, it flows differently, and we've learnt to listen. There's something quiet about the way science changes the world. Not with noise or thunder, but with a thought, a question, whispered into the stillness of a day. And sometimes, that whisper grows, gathering meaning, expanding into something that shifts everything we thought we knew. Einstein's realization about time didn't begin with equipment, or experiments, or laboratories full of blinking machines. It began with stillness, a desk, a tram rolling by a window, and a mind that refused to stop wondering. He was a young man then, not yet the famous figure we picture today. He worked in a patent office, reading technical documents, stamping approvals, but in his mind, something vast was unfolding. Not paperwork, but light and time. What would it feel like, he wondered, to ride on a beam of light? Not just look at it, not just study it, but move with it, become part of it. It's the kind of question that doesn't have an obvious answer, the kind that feels more like poetry than physics. But that's where the magic lives, in the blurry space between what is known and what is imagined. If you could ride a beam of light, you'd discover something strange from your perspective. The world around you would warp, distances would shorten, time would slow down, and if you moved fast enough, close to the speed of light, time for you would almost stop. This wasn't just fantasy, it was the seed of Einstein's special theory of relativity, published in 1905. In that paper he proposed something radical, that time is not absolute, and that the faster you move, the slower time flows for you, at least from the perspective of someone standing still. Imagine two twins, one stays on Earth, the other boards a spaceship, and travels near the speed of light, then returns. The traveling twin would come back, younger. Not by magic, not by illusion, but because time passed differently for them. This became known as the twin paradox, and it was just the beginning. But Einstein didn't stop there. Because movement through space wasn't the only thing that could bend time. He began to think about gravity, not as a simple force, but as something more elegant. He imagined a massive object, like the sun, sitting on the fabric of space, and just like a heavy ball on a stretched sheet, it would curve that fabric near the sun. Space would be curved inward, and so would time. This idea became the heart of his general theory of relativity. Published in 1915, it proposed that what we call gravity isn't a pull, it's the result of space and time being curved by mass and energy, and that curvature changes everything. Time, he realized, ticks differently depending on where you are in a gravitational field. closer to the source. Time moves slower, farther away. Time speeds up. It's a truth so subtle, so quiet, you'd never feel it. But it's there, whispering through every moment. This was more than theory. It was a new map of reality. A map where time could stretch and compress, like soft fabric caught in invisible hands. In 1971, decades after Einstein's insight, scientists put it to the test. They flew atomic clocks on planes and compared them to clocks on the ground. When the clocks returned, they were different, by tiny amounts, but exactly what Einstein had predicted. And now, every day, satellites orbiting above us, farther from Earth's gravity, tick just a bit faster than the clocks down here. If we didn't correct for this, your GPS wouldn't work. Planes would drift off course, maps would be wrong. The difference is only microseconds, but it adds up fast. And we fix it by trusting Einstein's quiet thought. It's easy to imagine science as something loud, labs buzzing, equations flashing, headlines declaring breakthroughs. But some of the most powerful truths arrive like this. Softly, in the mind of someone sitting still, asking what light might feel like if you could touch it. Einstein didn't set out to change the world. He followed curiosity. He followed wonder. And he trusted that even the strangest ideas could reveal something true. And now, those ideas shape your day, whether you notice or not. When you unlock your phone, when a satellite guides your car, when you sit still and wonder why time feels different on vacation, in the mountains, by the sea, maybe it's just mood. Maybe it's your schedule, but maybe, just maybe, time really is moving differently. Measurably, quietly, gently. Einstein's realization didn't end with clocks or formulas. It opened a door, one we're still walking through. Gravity isn't just weight. It's time, bent and folded. It's the universe, reshaping the rhythm of now. And as you rest, your own body is part of that rhythm. Your breath, your pulse, your presence, each second slightly sculpted by the gravity that holds you. The earth, beneath your bed, is slowing your time, ever so slightly, and somewhere high above on a mountaintop, or floating in orbit, another second is beginning just a little sooner. And that's what Einstein showed us. That time isn't a rule, it's a response, a delicate thread, stretched by speed and curved by gravity. So as you drift now into sleep, remember that even in stillness, you are moving through something quietly magnificent. You are wrapped in time, and time is moving with you. If you've ever looked up at the sky and felt something different, a kind of spaciousness or light, or quiet awe, you're not imagining it. Something is different up there. Not just the air, not just the view, but time itself. It ticks just a little faster in the sky. This isn't poetry, it's physics. And tonight, we'll let that idea unfold, slowly, gently, like a cloud passing overhead. To begin, imagine a clock, a perfect clock, not digital, not ticking hands on a dial, but an atomic clock, the kind that counts time by the vibration of atoms. Reliable, exact, the kind of clock that doesn't drift by even a billionth of a second, unless something unusual happens. Now imagine you place two of these clocks in the same room. They tick in perfect sync, down to the smallest measurement. But then, you take one clock upstairs, just a single floor higher, or maybe you fly it on an airplane, or place it in orbit, far above the Earth. What happens? The clock that was moved ticks faster. Not by much, not enough to notice with your eyes or ears, but enough to measure, enough to matter. This is gravitational time dilation at work. The idea that time flows at different speeds depending on how deep you are inside a gravitational field. Earth's gravity is strongest near the surface. The farther you move away from that center of mass, the weaker the gravitational pull becomes. And where gravity is weaker, time runs just a little quicker. So when you rise into the sky, even by a few meters, even for a few hours, your time gently slips ahead. It's a soft, quiet lead. Not a race, but a rhythm, slightly altered. And here's the beautiful part. We use this knowledge every day. You've probably never held an atomic clock, but if you've ever used GPS, you've trusted one. There are dozens of satellites orbiting above us, each carrying atomic clocks, each zipping through a place where time flows faster than it does down here. To keep GPS accurate, we must constantly adjust for that speed up. Otherwise, every direction would drift. A few nanoseconds of misalignment could send your map miles off course. So engineers, without fanfare, account for Einstein's equations every second. The clocks in space are corrected to match the ones on Earth, or rather the ones on Earth are slowed down, ever so slightly, by gravity. This constant adjustment is proof that time doesn't flow the same everywhere. The satellite is just a bit ahead, and we here below are always a bit behind. Now, think about that for a moment. You might be lying in bed right now, still, quiet. Listen above you. Perhaps 12,000 miles up, a satellite is spinning, and its time is moving faster than yours. Not because it's hurrying, not because it's in a rush, but because it's farther from Earth's gravitational grip. Because the sky, somehow, is freer, and that difference, that invisible drift is real, constant, measurable, inevitable. It's a reminder that even stillness contains motion. Even silence holds structure. Gravity, though invisible, is always working, shaping not just the arc of a falling stone, but the flow of a second. This idea isn't just theory anymore. It's a quiet law, tested with airplanes, proven with satellites, written into every app that guides you home. In one experiment, scientists took 2 atomic clocks and flew one around the world on a jet. When they reunited the clocks, they were no longer in sync. Time had flowed differently for the one that flew. And if we launch a clock into space, say to the International Space Station, it ticks faster because it's higher, but also slower because it's moving quickly. That's the strange balance of relativity. Movement slows time. Distance from gravity speeds it up. So astronauts orbiting Earth are caught between 2 effects, and their time dances between them. It's a reminder that time is not simple. It's shaped, bent, woven with space, and it responds to where you are and how you move. It might feel unsettling at first to learn that time is so flexible, but I think it's beautiful. It means the universe is not mechanical. It's not made of rigid gears and absolute measurements. It breathes, it responds, it moves with you. And when you rise into the sky, you step into a place where that breath is just a little bit longer, a little more spacious, a little faster. It's easy to forget how strange the world really is. We live in schedules, alarms, clocks, reminders. Seconds feel solid, minutes feel owned. But science reminds us that those units are local, defined not by certainty, but by where you are in the curve of space-time. Time flows differently on the moon. It flows differently inside a black hole. It flows differently on the second floor of a building. So what does that mean for us? Maybe nothing changes. You still get up in the morning. You still go about your day. But maybe, when you fly in a plane, when you hike up a hill, when you stare out the window during takeoff, you'll remember that in that moment, just briefly, you are moving through time a little differently. And no one else on Earth will share those exact seconds, in that exact rhythm, in quite the same way. And that's worth remembering, even as you fall asleep. Because tonight, as you drift deeper, your body relaxes into the Earth's gravity. Your time slows, gently, imperceptibly, and somewhere far above in the quiet dark of the sky, a clock ticks just a little bit faster. And everything in the universe carries on, softly, quietly, different. We often think of gravity as something heavy. It keeps our feet on the ground, holds the oceans in their place, pulls apples from trees. It's the reason things fall when you drop them, the reason the moon circles the Earth and the Earth circles the sun. But gravity does more than shape motion. It also shapes time. This isn't something we feel in daily life. The minutes pass as they always do, or so it seems. But underneath that steady rhythm is something softer, stranger, and very real. Gravity gently squeezes time, and the stronger the gravity, the slower time flows. This idea comes from Einstein's theory of general relativity. He showed that massive objects like planets and stars don't just pull on things the way a magnet pulls on metal. Instead, they bend the fabric of space and time, like a heavy ball sitting on a stretched sheet, creating a dip that changes how nearby objects move. But it's not just space that gets curved, time bends too. And the deeper you are in that curve, that gravitational well, the slower your time will flow. This effect is called gravitational time dilation. It happens everywhere, all the time. But it's most noticeable when we compare clocks in different places. One clock deep in a gravitational field, say near the surface of the Earth, will tick more slowly than a clock positioned farther away, where the gravitational pull is weaker. Scientists have tested this with incredible precision. They've placed atomic clocks at the base and top of tall buildings. They've flown them on airplanes. They've sent them into orbit. And each time the results agree. Clocks closer to a source of gravity run more slowly. This means that time isn't moving the same for everyone. Someone living at sea level is aging just a tiny bit more slowly than someone living high in the mountains. Not by years or even days, just tiny fractions of a second, far too small to notice, but they're real, and they accumulate inside your own body. The same thing is happening. Your head is slightly farther from the center of the Earth than your feet, and so your face is aging just a little bit faster than your toes. It's a quiet reminder that time flows differently, depending on where you stand. Gravity does not just hold us down, it shapes our seconds. It stretches moments. It makes the experience of time dependent on position, on distance, on mass, and the more massive the object, the stronger the effect. A white dwarf star bends time more than Earth. A neutron star bends it even more, and a black hole, the most extreme example, slows time to the point that it nearly stops. If you were to float just above the surface of a black hole, your clock would tick so slowly compared to someone far away that it would appear to them that you had almost frozen. To you, everything would feel normal, but from a distance, your seconds would be stretched nearly flat. It's difficult to picture. Our minds aren't used to thinking about time as flexible, but it is, not metaphorically but physically, measurably, and gravity is the quiet hand that bends it. Even here on Earth, that bending shapes the way we keep time. Our most accurate clocks, atomic clocks, are so precise they can detect the difference in time between one step and the next. Raise the clock just a few inches, and it begins ticking faster. Place it in a valley, and it slows. Place it on a mountaintop and it speeds up again. This subtle squeeze of time happens everywhere. It's constant, invisible, and soft, like a hand resting on your shoulder, always there, always shaping the way the present unfolds. And though it doesn't change our schedules or our sense of now, it matters deeply to the way the universe works. It shapes how stars burn, how planets orbit, how light bends around galaxies. It means there is no single shared now. Every point in space experiences time differently, and we are all moving through our own personal streams of seconds, guided quietly by gravity. We usually think of gravity as a force that pulls us downward, but that's just how it feels from here. What it's actually doing is curving the path of everything, including time. So the next time you walk up a hill or stand at the top of a building, remember, time is flowing just a little bit faster up there than it is down below. The Earth is not only holding you to its surface, it's gently shaping your time, bending each second, pressing softly on the fabric of what you think of as now. And you, whether you feel it or not, are part of that flow. Imagine two identical clocks. They begin their lives perfectly synchronized, built the same, ticking in unison, keeping time with atomic precision. You place one on your desk. It stays there, still and steady. You take the other on a journey. Not across space, but through the curves of gravity and the shifts of speed. And when they reunite, something remarkable has happened. They no longer agree. The traveling clock has drifted, not broken, not faulty, just changed. Its seconds, stretched or compressed, have unfolded along a different path. This is the quiet truth behind what physicists call time dilation. And when applied to living beings, not clocks but people, it gives us one of the most poetic results in all of science. The twin paradox. The idea is simple to describe, but deeply strange to accept. Take two identical twins. One stays on Earth living a normal life. The other boards a spacecraft and travels far away at a high speed, near the speed of light, and then returns. When the traveling twin steps off the ship, they're younger. Not metaphorically, not emotionally. Measurably, the twin who remained behind has aged more. Their clock and their body moved through more time. The paradox lies in this symmetry. At first glance, each twin should see the other as moving. So why doesn't each twin think the other should be younger? The answer rests in acceleration. The traveling twin turns around, changes frames. They experience the shift, the change in direction, and that change breaks the symmetry. This isn't just a story. It's been tested. Not with human twins flying to distant stars, not yet, but with particles. Certain unstable particles, like mu-aries, decay very quickly. Their lifespans are measured in microseconds, but when we accelerate them to near light speed in particle accelerators, something amazing happens. They last longer. They decay more slowly. Their inner clocks, the ticking of their lifespans, stretch out, and this aligns perfectly with Einstein's prediction. Time dilation isn't a theory waiting to be proven. It's already part of the machinery of modern physics, and it becomes even more elegant when we think about gravity. Imagine now that our two clocks aren't traveling through space, but resting at different altitudes. One is deep inside Earth's gravitational field, in a valley, perhaps. The other is placed higher, on a mountaintop, and we leave them there, just sitting, ticking, waiting. After enough time passes, we compare them, and once again, they disagree. This time, the clock on the mountaintop has moved faster. It's not because of speed, but because of height. The higher clock was farther from Earth's center of mass, gravity's grip was looser, and so time flowed just a little more freely. What this tells us is profound. Time isn't one single stream. It's not a universal tide pulling us all forward together. Instead, it's like a vast, slow-moving ocean, with different depths, different currents. Every person, every clock, every moment floats through a slightly different patch. You and I, though still, though calm, are drifting through time at subtly different rates, and those rates depend on where we are, how fast we move, and how deeply gravity holds us. The twin paradox reminds us that motion and gravity aren't just about distance and force. They shape the very experience of reality. Imagine you could climb to the top of a very tall tower, high enough that gravity noticeably weakens. You bring a perfectly synchronized watch, set to match your friends on the ground below. You stay up there for a year, and when you return, your watch shows more time than theirs. You've aged slightly more. Or imagine standing next to a black hole. You don't fall in, just float nearby, held at the edge. Your twin stays far away, in the safety of space. For you, minutes pass. For them, perhaps years. When you finally return, they've aged, and you have not. It's not imagination, it's how time behaves under extreme gravity. And the reason this all works is because time is not separate from space. They're linked, woven into something called space-time, a four-dimensional fabric, where every point has three directions of space and one of time. And when that fabric bends, due to mass, due to speed, everything embedded in it changes too, including clocks, including life, including you. The twin paradox isn't just a curiosity. It's a window into how the universe measures change. In daily life, we don't feel these differences. The shift in time between your feet and your head is too small to notice. But with sensitive tools, with atomic clocks and satellites and laser beams, we can detect them, measure them, and build systems that depend on them. GPS, for example, only works because we correct for the time differences caused by gravity and motion. The satellites high above Earth are moving fast and orbiting in weaker gravity. Their clocks tick faster than ours, and if we didn't account for that, our location data would become wildly inaccurate in just minutes. So we adjust. We bend our understanding to match the bending of time. And that bending means something more. It means that the universe is responsive. It means that time is not absolute. It flows in ways shaped by matter, energy, and perspective. No two clocks agree. Not perfectly. And that's not a failure. It's a feature. Every clock is tied to its place in space-time, its location, its history, its motion. The more we study this, the more precise our tools become. Clocks now exist that can measure a difference in time from the bottom to the top of a single stair step. It's no longer just mountain to valley. It's room to ceiling. It's desk to shelf. Time dilation isn't just happening in labs or in orbits. It's happening in your home, in your body. We are all part of this subtle stretching. The twin paradox reminds us that even when two people share everything, genes, birthdays, names, they may still age differently if their paths through space-time are not the same. And that opens up a new way of thinking. Time is not a thing that happens to us. It's something we move through, shaped by how we exist, your memories, your heartbeat, your breath. Each unfolds along your own personal curve of time, and that curve is bent gently by where you are and how you move. Somewhere in the future, we may build spacecraft that travel fast enough to make the twin paradox a daily experience. The journey across stars could stretch time so that a few months aboard feel like decades on Earth. The travelers return to a changed world younger than the children they left behind. It sounds like science fiction, but it's already science fact, just waiting for the engineering to catch up. Until then, the paradox lives quietly in our satellites, in our clocks, in the soft divergence of time that happens all around us. The next time you check the time on your phone, on a wall, in your mind, remember that no two clocks anywhere are ticking in exactly the same way. Even the most synchronized twins, clocks or people, will always drift apart if they follow different paths through this strange flexible fabric we live in. Time is not fixed. It's personal, curved, bent, and quietly dancing beneath our feet. The hum is soft, a low, constant vibration beneath the metal floor. You don't really notice it unless you stop thinking. But in space, silence is rarely still. There's always something moving, always something whispering against the hull. She floats, arms gently folded across her chest. Not strapped in, not rigid, just adrift. The cabin lights are dim, her eyes are closed, her breathing is slow. In this moment, the astronaut is not piloting, not observing, not recording. She is sleeping, and time is moving differently for her. This isn't metaphor. This isn't about dreaming or the psychology of sleep. This is physics. As she sleeps in orbit, about 250 miles above the surface of the Earth, the seconds are flowing just a little bit slower for her than for anyone asleep in a bed down below. It's not a trick of light, not a delay in signal. It's real, measurable, constant. The astronaut, in this quiet, drifting rest, is experiencing time dilation. She's affected by two things: her altitude and her speed. Up here, gravity is weaker than on Earth's surface, and in weaker gravity, time ticks faster. But she's also moved very fast. The International Space Station orbits Earth at roughly 17,500 miles per hour, and at those speeds, another form of time dilation occurs. One caused by special relativity. Motion slows time, so the astronaut experiences both effects at once. One trying to make her time flow faster, the other trying to slow it down. For astronauts aboard the ISS, the net effect is a slight slowing. When they return to Earth, after months in orbit, they are younger by a fraction of a second than those who remained behind. It's not much, less than a blink, but it's real. She drifts in her sleep, her mind somewhere between memory and dreaming. And outside, the Earth turns slowly below her. Each orbit takes about 90 minutes. 16 times a day, the sun rises and sets for her. Light to dark, dark to light. It's a strange rhythm, one that makes the idea of night feel meaningless. Instead, there is only now, and the now is different than the one on Earth. Mission Control marks the passage of time in Coordinated Universal Time, UTC. But up here, time is curved. Atomic clocks onboard the ISS run slightly out of sync with those on the ground. And if we didn't constantly correct for it, data would drift, signals would slip, navigation would fail. But we do correct, quietly, constantly. Relativity is part of the software, built into the math. As she sleeps, her body obeys a slightly different clock. Her heart beats just a little off beat from what it would be on Earth. Her dreams unfold across a timeline that's not quite in sync with the world she left. In deep sleep, her body repairs itself. Cells divide, tissues rebuild, metabolism slows. But all of these processes are taking place in a reference frame slightly offset from the rest of humanity. And yet, it feels normal. This is the strange part. Relativity doesn't make you feel faster or slower. It doesn't give you a sensation of stretching or lag. You are always the center of your own timeline. Always at rest in your own world. It's only when compared to someone else that the difference emerges. And so, down on Earth, someone else sleeps. Perhaps her twin. And over the months, as they both rest, the astronauts' seconds are stretched just a little longer. No alarms ring, no bells toll. Just the soft passage of time, bent. It's easy to think of physics as cold, equations and measurements and logic. But there's something tender in this image. The sleeping astronaut, held in orbit, rocked by the soft curvature of space-time. But gravity is not pulling her down, not dragging her to Earth. Instead, she is falling, constantly, but never landing. Her path curves with the planet, circling again and again. And because she moves so fast, her time bends inward. If she stayed up here for years, if she circled long enough, and then returned, she would find that Earth had aged more than she had. She would walk through a future that arrived faster than her own clock. The astronaut's experience becomes a quiet proof that time is not universal. It bends. It flexes. It flows differently depending on how and where you drift. The International Space Station is a kind of laboratory for this truth. It carries not just people but clocks, and those clocks must account for relativity in every measurement they send back. It's not science fiction, it's operational necessity. We measure how GPS satellites experience time dilation. We adjust their signals. We build corrections into spacecraft systems, and we prepare astronauts for the knowledge that they return, just a little younger than their age suggests. This isn't about immortality, it's not about escaping aging. But it does reveal something poetic that, by moving fast enough, or climbing high enough, you can slip just slightly into a slower stream of time, and when that motion is quiet, like a sleeper's drift in microgravity, it feels even more delicate. The astronaut's sleep is peaceful, the silence of space outside, the gentle hum of systems inside. Her body, suspended, her seconds slightly stretched, and all the while, Earth continues its rhythm. Oceans rise and fall. Traffic lights flicker. Children grow. News passes. Seasons shift. And her clock drifts behind. Fractionally, but undeniably, even her heartbeat, recorded by mission telemetry, tells a story not quite in sync with the ground. In this difference is a reminder we are never perfectly aligned. Every location, every motion, brings with it a shift in how time unfolds. The astronaut's journey shows us that, and though she may not feel it, she carries it home. Every astronaut returns to Earth slightly younger than they would have been had they stayed. The difference isn't enough to matter to birthdays or calendars, but it matters to physics. It confirms the fabric is flexible, and that sleep, motion, altitude, they all touch the thread. In another mission, a pair of real-life twins helped explore this truth. NASA's twin study sent one brother into space for nearly a year, while the other remained on Earth. Their genetics were identical, but their environments were not. And though the effects of microgravity were the focus, the relativity of time was there too. The orbiting twin aged just a little less. Our sleeping astronaut may not think about that as she rests, but she is living it. Her dreams unfold inside a capsule carving its path through curved space-time. And each loop adds a little more difference. Each hour in orbit, a small step away from the timeline below. If she stayed in space long enough, the difference would grow. She might return to a future just slightly farther ahead than the one she left. And yet, to her, time always feels normal. This is the beauty of relativity. No matter how stretched or compressed, your time always feels like time. Your seconds never feel longer or shorter. Your life flows with perfect rhythm from your point of view. Only in comparison does the bending appear. And so, in orbit, as Earth spins silently beneath her, our astronaut sleeps, and the clock ticks, differently. But not wrong, not broken, just curved. A reminder that time is not a rigid ruler. It's a fabric, and she is sleeping in its folds, deep beneath the waves, past the reefs and the scattering schools of light-chasing fish. Below the thermoclines and the shifting shades of blue, there is a quiet unlike any found on land, a pressure that presses inward, a darkness not empty, but full of stillness, full of weight, full of time that changes here. On the ocean floor, a clock ticks. Not loudly, not fast, but differently. Not because it's broken, not because it's wet, but because it is deep. So deep that gravity itself is holding it more tightly than it holds you now. And in that pressure, in that closeness to Earth's center of mass, time begins to slow. Not by hours, not by minutes, but by the faintest whisper, a few billionths of a second slower than time on the surface. But still slower. This is gravitational time dilation, felt not in space, but in reverse. Because while astronauts soar upward, feeling time stretch slightly outward in orbit, the ocean floor does the opposite. It pulls time in, closer to Earth's core. Gravity is stronger, just enough to alter the rhythm of seconds, just enough to make one moment last a breath longer than it would above sea level. Imagine two identical clocks. One is placed at the summit of a tall mountain, the other is lowered into the deepest trench in the ocean, the Mariana Trench, nearly 7 miles down. If you let them run, undisturbed, then bring them back together, they will disagree. The clock from the ocean floor will have ticked fewer times. Its moments passed more slowly, its seconds were stretched softly by gravity, even though it sat perfectly still, even though nothing broke. The very structure of time was curved more deeply around it, and this, too, has been tested. Scientists have used atomic clocks sensitive enough to detect time dilation from just a meter of elevation, from one floor of a building to another, from shelf to desk. If those slight differences are real, then so are the shifts beneath the sea. Not just theoretical, not just poetic, measurable. We often think of the ocean as timeless, unchanging, an ancient rhythm of tides and waves. But beneath that rolling surface is a gradient of time, each layer of depth flowing ever so slightly slower than the one above it. A diver, descending, is entering deeper time, and though the difference may never be felt, it is still there. Recorded, stored, subtle. Somewhere on the seafloor, there could be a small box, a watertight case containing a precision clock, counting seconds in silence, and above it, on a ship, another identical clock, ticking faster, each click of its atom-aligned mechanism, pulling slightly ahead of its underwater twin. The difference, nanoseconds per day. But over weeks, over months, the two clocks part ways, a slow divergence written in gravitational curves. The deeper you go, the slower you are. This isn't just about height. It's about proximity to mass. Earth's mass pulls more tightly at its center, and time follows the curve of that pull. At sea level, you're already deeper in Earth's well than someone atop a mountain. And, on the seafloor, you're deeper still. Gravity doesn't just shape how objects fall. It sculpts how time flows. This truth is built into GPS satellites, which orbit high above Earth's surface. Their clocks are corrected for the faster time they experience in orbit. But what about submarines? What about deep-sea sensors? If we built a global timing system that stretched from space to the ocean floor, we'd have to adjust for every vertical inch, because time, at every level, is not the same. In this way, the ocean becomes more than water. It becomes a curve, a living map, of stretched and compressed seconds, and all across it, time unfolds in layers. On a coral reef near the surface, time flows just a bit faster than it does 300 feet below. At the edge of a drop-off, faster than the caves that tunnel through deeper stone. And at the bottom, where the light fades, where the pressure crushes, where only strange glowing creatures drift through the cold, time is slowest. This doesn't change how fish swim. It doesn't affect how a jelly pulses. Life carries on in rhythm with itself. But when compared to the world above, it all ticks just a bit behind. You might wonder why this matters. Why measure such small differences? What does it change? But the ocean teaches us that even small things accumulate. A difference of 1/1000th of a second might seem like nothing, but when layered over years and across global systems, those billionths add up. Synchronizing communication between satellites and submarines, between seafloor observatories and surface ships, requires accounting for the curve. We've learned to do this, to build the bending of time into our technology. But the beauty is deeper than the tools. It's in the understanding that time, what we thought was flat, is actually shaped, and the shape continues beneath the waves. The pressure down there is immense, over 1,000 times the pressure of air at sea level. But pressure is not the same as gravity. It comes from the weight of the water above, not from being closer to the Earth's center. And yet, the result is the same. The deeper you are, the more gravity wraps around you. And the clock at the bottom ticks more slowly. This isn't something new. Einstein predicted it over a century ago, but it's only now, with our most delicate tools, that we can observe it this closely. And we are observing it. Scientists are placing sensors at ocean depths to monitor seismic shifts, to listen for tsunamis, to study the quiet pulses of Earth itself. And inside those sensors are clocks, tracking every tick of data. Their rhythms are shaped, not just by their electronics, but by the depth at which they sit. And so, in every recording, in every timestamp of deep ocean research, is a hidden fingerprint of curved time. It's not an error. It's not noise, it's truth. The Earth is bending time, and the ocean is part of the curve. If you could build a tunnel from the seafloor to the stars and drop clocks along the way, you would see a smooth, continuous shift in the way time unfolds. Slower at the bottom, faster at the top, and perfectly curved in between. And you, wherever you are, whether high in the mountains or lying close to the sea, are caught in that shape. Your moments are shaped by the pull of the planet. Your seconds are stretched or squeezed by how close you are to its center. And beneath you, in the quiet dark of the ocean, time is moving just a little slower. A reminder that even in silence, even in places we rarely go, the fabric of the universe is always shifting. The ocean floor is not just a place. It's a part of time's geometry. And the clock that ticks down there, slow as it may seem, is writing the same story as the clocks in orbit above, only at its own pace, its own gentle rhythm, its own place in the curve. And so, somewhere, a tiny tick echoes through salt and stone, a slow heartbeat of time. At the bottom of the sea, there is a kind of sound that doesn't travel through air. It doesn't move like a wave across the surface of water. It doesn't vibrate the way a guitar string hums when plucked. This sound is older, stranger, and far more quiet than any we've known. It is a ripple in the fabric of the universe itself. This sound is a gravitational wave, and when you hear one, not with your ears, but with instruments tuned to the deepest motions of space, you are not simply listening to something that happened. You are listening to time being changed. Gravitational waves are not made easily. They come from events so massive, so violent, so far beyond normal scale, that they reshape the very structure of space-time as they occur. Two black holes spinning toward one another, faster and faster, until they collide and merge into one, a neutron star collapsing. The early shudder of the universe itself, just moments after its birth. These are the moments that generate gravitational waves, and when they travel, they do not carry sound in the traditional sense. They carry movement. They stretch and compress space itself as they pass by. And in doing so, they bend time. But not in a way you would feel if one passed through you. Your body wouldn't stretch. Your heartbeat wouldn't skip. You would feel nothing at all. And yet, everything about your timeline would be changed. even if only slightly, for the briefest of moments. Time, like space, is not fixed. It can be squeezed. It can be stretched. It can ripple. Gravitational waves are the proof. For decades, they remained theoretical, predicted by Einstein, but unobserved. The ripples were believed to be too small, too faint, lost among the noise of ordinary matter. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, changed everything. Two detectors, located thousands of kilometers apart, recorded the same pattern of stretching and compression, an echo from the distant collision of two black holes over 1 billion light-years away, a ripple in space-time, strong enough to reach Earth, and subtle enough to move LIGO sensors by less than the width of a proton. It was not sound, yet it could be translated into sound, a rising chirp, a signal that, when processed, could be heard as a faint blip in audio form. And though our ears didn't feel it, our instruments did, and they confirmed the waves passing. That signal was time, folded and unfolded. A brief moment when our timeline was not entirely our own, a moment when something from across the cosmos brushed past us and altered the pace at which our seconds flowed. This doesn't mean time stopped, or reversed, or disappeared. But it does mean that for a moment, the rhythm of everything shifted, just slightly. The tick of the most precise atomic clocks slowed, and then returned. The shape of space twisted and then relaxed. And through it all, we kept moving. Not because we resisted the wave, but because we were part of it. When a gravitational wave passes through you, you are not separate from it. You are within it. You ride the ripple. Your seconds and your space stretch as one. This raises a strange question. If time can be altered in this way, does that mean we can hear it? Not just record it, but sense it. Instruments like LIGO are designed to detect these fluctuations with incredible precision. They use laser beams traveling down long arms reflecting off mirrors, returning back to be compared. If a gravitational wave passes, it alters the distance the beams travel, ever so slightly. The interference pattern shifts, and a signal appears. But that signal is not a wave in sound. It's a wave in space-time. Yet, when scientists translated that signal into audio frequencies, they found something beautiful. The pattern could be played through a speaker, a real, audible chirp, a cosmic signature turned into sound. You can listen to time change. The wave that caused the first detection took over 1 billion years to reach Earth. It had traveled all that distance, through galaxies and voids, untouched, unchanged, until it passed through us. And when it did, it left behind a memory, a whisper in our clocks, a story in the silence. This isn't just poetic, it's measurable. Our best clocks can detect the impact of gravitational waves, not directly like LIGO, but through their timing. Networks of pulsars, rapidly spinning neutron stars, send radio pulses across space with incredible regularity. When a gravitational wave moves between a pulsar and Earth, the timing of those pulses shifts, just slightly, just enough to mark that something vast has passed between us and the stars. This is called a pulsar timing array, a way of listening to the deep structure of time, not with ears but with pattern and rhythm. And the rhythms tell us time is not flat. It is always being stirred, and in every stirring, time is bent. By black holes, by collapsing stars, by the weight of invisible events. And when we hear those waves, we are not just hearing space being bent, we are hearing the stretching of seconds, the movement of time itself. It is humbling to realize that something happening billions of years ago can still touch our present, not through light, not through particles, but through the very structure of reality. When a gravitational wave passes, it does not carry sound in the way we know it, but it does carry change, and that change is detectable in the language of time. For a brief moment, everything slows or stretches. The rules do not break, they bend. You can't see it happen, you can't feel it, but the Earth itself moves. Its surface shifts, its space grows and shrinks by the tiniest amount, and then it returns to stillness. But that stillness is never perfect. More waves are always on the way. They are all around us, passing through us constantly. But only the largest, the closest, the most dramatic, are detectable. Most waves go unnoticed. They ripple through the universe, without trace. And yet, they shape the way time flows everywhere. So can you hear time in a gravitational wave? Not directly, not as a voice or melody, but you can listen to its trace. Its imprint, the echo it leaves behind in the clocks, and the beams and the stars. You are not outside this process. You are part of the same fabric. Your life unfolds along the same curves, and if a gravitational wave changes the shape of space-time, then your seconds, your very experience bends with it. Gravitational waves remind us that the universe is never perfectly still, that space and time are alive with motion. Even the most silent reaches of space, the coldest voids, are vibrating softly with the memory of things colliding, and those vibrations travel forever. No medium to slow them, no friction to stop them. Only expansion, only distance, only time itself as the carrier. As you rest, imagine this. The world around you, though quiet, is not unmoved. A wave from some distant merger may be crossing through you right now. You don't notice. You won't feel a thing. But your seconds, if counted finely enough, would show the mark. A moment bent. A curve within the curve. This is how gentle the universe can be. Its most powerful signals arriving not as crashes, but as sighs. Not all waves are loud. Some are made of silence. And in that silence, time shifts, and we listen. Imagine standing at the edge of something so dense, so heavy, so complete, that even light cannot escape it. You are not falling in, not yet, just hovering, weightless, silent, staring into the dark. This place is the event horizon of a black hole, and just beyond it, time itself begins to behave differently. Black holes are not just holes. They are not empty. They are not tunnels. They are regions of space-time wrapped in their own gravity, so strong that the rules we know bend and twist, until they nearly break. And at the center of it all, time ceases to behave the way we understand it. You might wonder how that can be. How can something as constant as time, the very thing that keeps your heart beating, your thoughts unfolding, how can that stop to understand? We need to think, not in seconds, but in curvature. Everything with mass bends space. This is what Einstein showed us. Mass tells space how to curve, and curved space tells matter how to move. The Earth bends space around it, and that's why the Moon orbits. The Sun bends space more, and that's why we orbit the Sun. Black holes. They bend space so sharply, so violently, that the curve becomes a wall, and that wall is not made of rock or fire. It's made of time. To an outside observer, something falling toward a black hole slows down. As it approaches the event horizon, its clock appears to tick, more and more slowly. From far away, it never quite crosses the line. It just hovers at the edge, forever fading, its last seconds stretched out into eternity. But for the object itself, for the one falling in, time feels normal. Seconds pass as they always do. Heartbeat follows heartbeat. No warning bell rings. No alarm sounds. They cross the horizon, and there is no turning back. No return. No message sent home. Inside the event horizon, all paths lead inward, not just in space, but in time. This is where the strangeness deepens. In most places, you can choose where to go: forward, backward, left, right. You can resist gravity, jump, climb, escape. But inside a black hole, there is no direction that leads out. Every future, every path through time and space, points toward the center. This means that falling toward the singularity, the core of the black hole, is not like falling into a hole. It's like moving forward in time. You cannot stop yourself any more than you can stop the next second from arriving. And the singularity, the place where, as far as our math goes, the density becomes infinite, space collapses, time curls inward. The laws of physics, as we know them, no longer give clear answers, but something happens even before you reach that point inside the event horizon. the role of time and space reverse. Radial distance, the measurement from the center outward, becomes a time-like direction. You don't move through it by choice. You are carried, drawn, compelled forward, just as you are compelled to move into the next moment outside. This leads to the strange conclusion. Inside a black hole, you do not fall deeper into a place. You fall deeper into time. And time itself narrows, collapses, approaches a single point. So does time stop inside a black hole? From your point of view, falling in, no. Your clock keeps ticking. Your thoughts continue, at least for a while. But from the perspective of the outside universe, your time slows to stillness. Your moments stretch out longer and longer. And if someone could watch you really watch, they would see your fall frozen in time. This discrepancy is not an illusion. It is a feature of space-time itself, and it reveals something profound, that time is not absolute, not singular, not shared in the same way everywhere. There is no universal clock. Instead, there are infinite clocks, each tied to its own path, its own frame of motion and gravity. And black holes show us where that relativity reaches its limit. Inside a black hole, all of space becomes one direction, the one you cannot resist, and time itself folds inward. You might think of time as a river. Outside a black hole, the river flows gently. You drift downstream. You can paddle, pause, even float in place for a while. Near the event horizon, the current picks up. Your control slips away, and once you pass the horizon, the river becomes a waterfall, a plunge that no swimmer can resist. But unlike a real waterfall, this one is not made of water. It is made of time's geometry. As you fall, you feel no sudden jolt. You do not scream. You do not break. You simply continue along the only path available to you, deeper into the singularity, where the math stops making sense. From the outside, time ticks differently. An observer would see your image hover, dim, red-shifted, slowed. The light you emit would stretch into longer and longer wavelengths. You would fade from view, your time frozen, but you are still thinking, still counting seconds, until the moment your path ends at the singularity. And at that point, no further time exists for you to travel into. Not because of some explosive crash, but because time itself has run out. The line that defines your future ends. And yet, the rest of the universe carries on. The clocks elsewhere continue ticking, galaxies spin, stars are born. Your path through time has ended, but others continue. And so, to ask whether time ticks inside a black hole depends on who is asking. To you inside, yes. Until the singularity to those outside, no. Your clock has nearly stopped. And this difference is real, not a trick, not a glitch, but the natural result of extreme curvature in spacetime. Black holes are not just death traps. They are clocks made strange. They are regions where time and space do not behave the way we expect. They are mirrors, showing us that everything we thought was solid, even the flow of time, is flexible, bendable, fragile. They remind us that time is not a background. It is part of the structure of reality, and that structure can warp how our best theories still fail at the singularity. Relativity breaks down. Quantum mechanics has no firm grip. We are left with mystery. Some theories suggest time inside a black hole may not truly end, that beyond the singularity may exist some new region, some rebirth. Others say time ceases altogether, that the inside of a black hole is the ultimate endpoint of a timeline. We do not know. But what we do know is that black holes teach us something gentle. Even in their violence, they show us the limits of time, the shape of it, the places where it no longer flows the same. They show us that seconds are not universal, that moments can stretch or vanish, depending on where you are and how deeply gravity holds you. And they show us that endings may not be the same for everyone. A life falling into a black hole ends in a place where time stops. But for others, it's just another passing second. No clocks are perfect. And inside a black hole, there may be no clocks at all. Only paths, only curvature, only a silence, so deep that even time cannot pass through it. There is a world so close to the sun, so fast in its orbit, so soaked in light and gravity, that time bends differently across its surface. This is Mercury, the smallest planet in the solar system, and the fastest. It completes a full trip around the sun in just 88 Earth days, a year shorter than a season, a world locked in a strange rhythm, where motion and gravity twist the experience of time itself. If you stood on Mercury's surface, you would see the sun rise slowly, hang in the sky for an eternity, and then seem to reverse, sinking backwards before climbing again. This illusion comes from Mercury's unique spin, a 3-2 resonance with its orbit. For every 3 times it rotates on its axis, it completes 2 full orbits around the sun. This means that days on Mercury measured from one sunrise to the next last 76 Earth days, longer than a year on Mercury. And during that long day, as the sun looms low on the horizon, time on Mercury stretches, not in a way you would notice while walking, not in a way that affects your breath or pulse, but in a way that can be measured, detected, predicted by the quiet equations of relativity. Because Mercury orbits so close to the sun, it moves fast, very fast, about 48 kilometers per second. That's nearly twice as fast as Earth moves in its orbit. And at those speeds, special relativity begins to bend time. The faster an object moves through space, the slower it moves through time, at least from the perspective of an outside observer. This is not a trick of perception. This is built into the geometry of space-time. And it doesn't stop with speed. Gravity also plays a role. The closer you are to a massive object, the slower time moves for you. This is gravitational time dilation, and it happens on Mercury in full force. The sun's mass curves space-time steeply, and Mercury, being so near, is deep inside that curve. Clocks placed on Mercury's surface tick more slowly than those far away from the sun. This means that time on Mercury flows differently than time on Earth, or on Mars, or even on the Moon. These aren't differences that affect everyday life, but they matter when precision counts, and in physics, precision always counts. If you place 2 identical atomic clocks, one on Mercury and one on Earth, and left them to run, the Mercury clock would drift behind. Not because it's malfunctioning, but because it is obeying a different flow of time. It is deeper in the sun's gravity well, and it is moving faster in its orbit. Both effects combine to slow its experience of time compared to Earth. But here's where the beauty begins. We can calculate these shifts. We can measure them. When spacecraft fly close to Mercury, their instruments must account for the bending of time. Their signals, their trajectories, their timings, all must be adjusted to match the way time flows in Mercury's curved environment. If we didn't adjust for these effects, our measurements would drift, our predictions would break, and our maps of the planet would slowly become inaccurate. But by folding relativity into the software, by accepting that time is not universal, we gain precision. We gain understanding. Mercury becomes not just a rock in space, but a proving ground for the nature of time, and the evidence builds. We have observed how Mercury's orbit changes due to the curvature of spacetime. This effect, known as the precession of the perihelion, was one of the first clues that Einstein's theory of general relativity was correct. For centuries, astronomers tracked Mercury's motion and found that its orbit slowly rotated, an extra wobble that Newtonian physics couldn't explain. But Einstein's equations, which described gravity as the bending of spacetime, predicted that wobble perfectly. Mercury became the first celestial test of the idea that mass curves time. And so, around the fastest planet, we see both speed and gravity conspiring to shift the tempo of seconds. This isn't just academic. The difference in time flow matters when building models of the solar system, when sending spacecraft, when testing the limits of our physical theories. Because the closer you get to massive bodies, and the faster you move around them, the more time itself becomes part of the terrain. Mercury teaches us that time is not a background, it is not a fixed canvas, It is shaped by motion, by mass, by proximity to the sun. It's tempting to think of time as moving forward everywhere at once. But in truth, it flows like a river with eddies and currents. On Mercury, those currents run slower, and yet, if you stood on its surface, if you looked up at the sun and watched it shift slowly across the sky, you would feel no difference. Your heart would beat as usual. Your thoughts would move along their normal paths, because within your frame, time always feels normal. It's only in comparison that the bending becomes visible, and that's what makes this so remarkable. Our instruments are now sensitive enough to detect time's shifts across distances of meters, between mountaintop and valley, between orbit and surface, and between planets. We are building a map of time that stretches beyond Earth, and Mercury is one of its earliest markers, because it is small and close to the sun, and fast. It lives in a part of the solar system where time flows differently, and that difference, though subtle, shapes the way we navigate space. Our spacecraft must understand this. They must know how time bends as they pass Mercury, how signals stretch, how orbits shift, and in that understanding we confirm something deeper, that time is not the same everywhere, and never has been. The sun does not just give light and heat, it bends the fabric of reality itself, and Mercury, locked in a tight dance around it, is moving through time at a different pace than you or I. Not a pace we would feel if we could stand on its rocky ground, but a pace we can measure, down to billionths of a second. And in those billionths, we find meaning. We find confirmation that space and time are not separate. They are linked, woven into a single geometry that responds to speed and mass and movement. The fastest planet teaches us that speed is not only a measure of motion, it is also a lever on time, and gravity, though invisible, is not silent. It speaks through the way seconds pass. Together, speed and gravity create a clock that ticks uniquely, and that clock sits on Mercury, spinning around the sun, marking a different rhythm than the rest of the solar system. And still, it turns, and time, ever so slightly slower, turns with it. Stand up. Not for long. Not to stretch or to walk, just to notice something quiet happening inside you. Something you'll never feel, but something that is real. As you stand, the top of your head is farther from the Earth's center than your feet, only by a meter or two, but that difference changes the way time moves through you. This is not poetry. This is physics. Real, tested, measurable physics. Your feet are closer to the source of Earth's gravity, and because gravity bends time, the seconds at your feet pass more slowly than the seconds at your head. It's a tiny difference, so small that it took some of the world's most precise clocks to detect it. But it's there. Your body experiences a gradient in time, a vertical slope in the river of seconds. Einstein's theory of general relativity predicted this, and in recent decades, scientists have confirmed it with atomic clocks, so sensitive they can detect time dilation over a change in height of just 30 centimeters. In one experiment, researchers placed two atomic clocks on different shelves. Same room, same temperature, same pressure. Just a slight difference in elevation. And yet, they ticked differently. The lower clock ran slower, the higher one ticked ahead. A difference not in design or error, but in the structure of time itself. So now, think again about your body. Your toes are ever so slightly behind your nose. Your chest ticks at one rhythm. Your brain a hair faster. And yet, you never notice. Because all of your systems are moving together. Your neurons, your heartbeat, your breath. They are all part of the same frame, flowing along their respective timelines. Each affected in sync with its position. But if you could place perfect clocks at every point along your spine, from heel to crown, you would find a gentle staircase of time with each higher point ticking a little faster. This bending of time isn't unique to people. It happens across cities, across buildings, between mountaintops and valleys. The higher you go, the faster time moves, and the reason is simple. Gravity holds time back, pulls it inward, slows it. Your feet, being nearer to the source of that pull, are anchored more deeply in it. This isn't metaphor, it's measurable. And not just on Earth. On any world with mass, from the smallest moon to the heaviest star, time curves with gravity. Every hill, every dip, every rise in terrain is a shape carved into time's fabric. The stronger the gravity, the deeper the dip, and the slower time flows at the bottom. You might ask, why does this happen? Why should gravity affect time? The answer lies in the way general relativity views the universe. Space and time are not separate things. They are one connected fabric. Space-time and gravity is not a force pulling on objects, but a curve in that fabric. Mass bends the fabric, and everything, including time, follows the bend. Imagine placing a heavy ball on a rubber sheet. It sinks in, creating a well. A marble placed nearby will roll inward. Not because the ball pulls on it directly, but because the surface it sits on is curved. Now imagine that same sheet represents not just space, but also time. As you get closer to the heavy ball, closer to the source of mass, you also move deeper into the dip in time. That's what happens at your feet. They are just slightly deeper in the curve than your head. And so time moves more slowly there. You can't feel this. You can't see it, but it's real. And in the vastness of the cosmos, this small truth builds into larger truths. GPS satellites, for example, orbit above the Earth. Where gravity is weaker, their onboard clocks tick faster than those on the ground. And if we didn't correct for that, our GPS systems would read by kilometers every day. The Earth's gravitational field affects time in ways that must be accounted for. And it all begins with the same principle, that where you are changes how time flows. Now imagine lying down. In that position, your body is horizontal, and every part of you is closer to the same distance from Earth's center. The time gradient across you is flatter, almost negligible, but still present. The moment you stand, you stretch across a taller section of the time curve, not in a way that ages you differently, not in a way that splits your timeline, but in a way that confirms that every second you live is shaped by your position in the world. And that, in itself, is profound, because if time is not fixed, if it changes based on where you are, then so much else follows. It means that the history of a mountain peak is ever so slightly longer than the history of a cave below it. It means that if you spent your entire life on top of Everest, you would age just a bit faster than someone who lived their life at sea level. Not enough to matter day to day, but real. And the difference grows over long spans. Your head, always a little ahead. Your feet, just slightly behind. If this were your whole world, if all life evolved with such gradients in time, could biology adapt to them? Could organs become subtly tuned to their local tempo? We don't know, but the presence of the gradient tells us that time is not a flat surface, but a living field, responsive, textured, curved, and your body, every moment it stands, is stretched across that field. In a way, you are always leaning into the future. Your head sees it before your chest before your knees before your toes. Not by much, never enough to notice, but always there. A gentle cascade of moments, falling upward. This is the intimacy of relativity. Not grand cosmic collisions, but the quiet truth that you are taller than your time. And when you sleep, horizontal, your seconds soften into greater unity. Your body rests, not just in posture, but in temporal alignment. You return to the center of your own time field, and still, Earth spins, gravity holds, and the clock at your feet remains just a touch behind the one in your mind. Light is faster than anything else we know. In the vacuum of space, light moves at a constant speed, roughly 20,99,792 kilometers every second. It is the speed limit of the universe. No signal, no particle, no ripple in space can travel faster. And yet, even light must bow to the pull of gravity. Not by slowing down, but by bending, by curving, by surrendering its perfect straight line to the shape of space-time itself. We used to think light always traveled in a straight path. Then came Einstein, and his idea that gravity is not a force but a curvature of space and time. Mass bends space-time, and light follows that curve. It does not accelerate or decelerate, but it moves through a geometry that is no longer flat, and this, strangely, makes it appear to slow down. When light passes through a strong gravitational field, say near a star or a black hole, an outside observer sees it as taking longer to cross the same distance. Its path is stretched, its timing delayed, not because it has lost energy, but because the landscape it moves through has changed. This effect is known as the Shapiro delay, a real, measurable phenomenon. Imagine you send a beam of light to bounce off a planet near the sun, and then return to you. If you calculate the round trip based only on distance and the speed of light in a vacuum, you'll get one answer. But if you actually measure the time it takes, you'll find it slightly longer. The reason? Gravity has stretched the time that light must cross. It's not that light is traveling more slowly in its own frame. Within the curved region, light still moves at full speed, but from your point of view, its journey takes more time. This delay isn't large, a few microseconds in our solar system, but it's enough to prove that gravity shapes the very rhythm of light. And if gravity can change the path of light and affect the timing of that path, then in a sense, gravity is reshaping how light moves through time. You can see this in action when you look at stars near the edge of the sun. During a solar eclipse, when the sky darkens and the sun's glare fades, you can observe that background stars appear shifted from their true positions. The light from those stars has been bent, its path curved by the mass of the sun, and this bending means that the light took a slightly longer path to reach us, not by traveling slower, but by following a curved route through warped space-time. In this way, gravity does not grab light and slow it down, it alters the terrain beneath it, and light, faithful to that terrain, moves accordingly. You might compare it to a car moving at full speed across a flat highway. If the road becomes curved, the car still moves at the same speed, but the path it travels is longer, and so it takes more time to reach the same destination. This is how gravity stretches time for light. The journey becomes slower when viewed from a distance, even though, locally, light's speed remains untouched. But there's another wrinkle. Light doesn't just follow space, it follows time. And in strong gravitational fields, time itself moves more slowly. So when light climbs out of a gravity well, say from the surface of a neutron star, its frequency shifts, its energy drops. This is called gravitational redshift. Again, it's not that light becomes sluggish, it's that, as it escapes the slower region of time, its rhythm changes, the beat of its wave stretches, and this stretching tells us the light came from a place where time flows differently. A photon born deep inside gravity carries with it the signature of that gravity's effect on time. So yes, gravity alters how light moves through time, not by changing light speed, but by curving the stage it travels on, and by changing the rhythm of every tick and wave within that journey. This leads to some strange consequences. If you were near a black hole, watching a flashlight beam pointed away from the event horizon, you would see the light stretch, its color sliding to red, its signal thinning out, and if the flashlight were aimed across the horizon, you might never see it emerge, not because the light slowed, but because the warping of time dragged it away from your world. Even in less extreme environments, like Earth's surface, gravity slightly affects the behavior of light. Our instruments are now so sensitive, they can measure this delay in satellites and deep space missions. It's why GPS satellites need constant corrections, because the timing of light-based signals must be adjusted to account for the way time flows differently in orbit than on Earth. Light, being tied to time, cannot ignore these shifts. It is bound to the same curved geometry that holds everything else. But does this mean light experiences time? Not quite. Light has no mass, and in relativity, a photon has no proper time. That means from light's perspective, if you could imagine such a thing, its entire journey, from emission to absorption, happens in one instant. No seconds pass for the photon, no duration unfolds. But for us, watching from a distance, we see light travel. bend, stretch, and be delayed. And that delay tells us that gravity is changing, how time behaves along light's path. In the early universe, as space was dense and hot, light moved through an environment where gravity shaped everything. And today, as light from those early moments reaches us, we can see in its faint ripples how space-time evolved. Gravitational lensing, the bending of light by massive galaxies, lets us see around corners of the cosmos, revealing distant objects whose light has been stretched and delayed by the gravity of what lies between. And in every lens, in every delay, in every shift of frequency, there is a message that gravity and time are not separate, and that even light, the fastest thing in the universe, must respect their entanglement. So when you watch the stars, you are watching old light, moving through a field that has shaped its journey every step of the way. Some of that light took the long way, some passed near galaxies, curved and delayed, some climbed out of gravity wells, stretched and softened, but all of it carries time's mark. And gravity wrote that mark on every photon. So does gravity slow down light's journey through time? Yes. If by slow, you mean lengthen, delay, reshape, light still moves at the universe's speed limit. But the universe itself is not flat. Its curves, its dips, its warps, those are the roads light must travel. And sometimes those roads take longer than we expect. Not because light hesitates, but because time does not always run straight. Picture yourself drifting far from any star. No planets nearby. No galaxies in sight. Just open space. Dark and quiet. Stretching endlessly in every direction. This is not the vacuum of an empty room. This is deep space. Cold, vast, and nearly untouched by gravity. And here, in this lonely silence, something begins to change. Not in your heartbeat, not in your breath, but in time itself. You are floating in a region where gravity is weakest. The farther you get from massive objects, the less space-time curves. And as the curve flattens, time begins to expand. It's not that your watch suddenly runs faster, not that you feel a jolt or shift, but if someone were watching you from Earth, from a planet, from anywhere deeper in a gravitational field, they would see your seconds stretch out. This is gravitational time dilation in reverse. Near gravity, time slows. Far from gravity, time flows more freely. And in the vast openness of deep space, with no nearby planets, no stars to bend the fabric, no black holes pulling at your path, you are as close to free time as the universe allows. This does not mean time flows infinitely fast. There is no boundless rush of seconds, but compared to clocks on Earth, your time moves ahead. And if you could stay there, drifting in stillness, and then return home, you would find you had aged more than the people you left behind. A paradox, but only if you forget that time is not absolute. It never has been. This idea might feel strange, but it's one of the cornerstones of relativity. There is no universal clock, no master tick that every atom obeys. Instead, time is woven into space, and it stretches or compresses, depending on how space is shaped. Cheap space is smooth, flat, gentle in its geometry, and that gentleness lets time flow more freely. We don't always think of space as heavy, but near stars and planets, space curves inward. That curvature grips time, pulls it into itself, slows it, but far away, out beyond the reach of that grip, time relaxes. You can imagine time as a fabric, wrinkled and pinched near massive objects. Those wrinkles are gravitational wells. They hold time down, like weights on a blanket. When you remove the weights, the blanket smooths out, and time stretches flat. So deep space is not just dark and distant. It is spacious in more than one way. It gives room for seconds to unfold without interruption. And we know this is true, not just as theory, but through measurement. When spacecraft leave the solar system, their clocks drift compared to those we keep on Earth. Not because of mechanical flaws, but because they are moving into a different layer of time. Each layer closer to the sun, closer to planets, slows the seconds, and the outer layers free of those influences. Let seconds move ahead. The Voyager probes, now traveling through interstellar space, exist in this freer time. Their onboard instruments may be old, but they still tick, and those ticks drift slightly ahead of the clocks we use to monitor them. Not by minutes, not by days, but by fractions of seconds that align with Einstein's predictions. And if you could place atomic clocks on the edge of deep space, beyond the solar system, outside the Milky Way, they would confirm it, that time is faster there, more open. But this isn't only about speed. It's about experience, about the idea that your location determines your timeline. And in deep space, that timeline opens. Of course, no region of space is truly empty. The universe contains dust, fields, energy, ripples, but the further you drift from mass, the weaker its influence becomes. And with each step away from gravity, your clock accelerates compared to those still inside. What makes this idea powerful is not the size of the effect, it's the fact that the effect exists at all. Time is not an arrow that flies the same for everyone. It is a field, a landscape, with hills and valleys. And deep space is its broadest plateau. You are no longer climbing a hill of time like you would be near Earth, where gravity slows your every second. You are gliding on a level path, where the tempo of the universe is less restrained, and in that glide, you can imagine seconds stretching just a little longer, not in perception, but in physical truth. This matters not just for clocks, but for the future of exploration as we consider sending humans to the edges of the solar system, and eventually beyond. We must remember that time will not accompany them at the same pace it does for those who stay home. The farther they go, the less gravity pulls, and the faster their time flows. If they returned, they might have aged slightly more than their families on Earth. A reversal of the usual story, not a twin returning younger, but older, because the twin who stayed was closer to mass, closer to the slow place of time. This difference is tiny, but in a universe that spans billions of years, and distances beyond imagination, tiny differences can accumulate, and they already do. The cosmic microwave background, the oldest light in the universe, is not just a signal of heat, it is a signal of time. It has traveled for over 13 billion years, and in doing so, it has been stretched by the expansion of space, and in a sense, that stretch reflects how time has changed its texture. In regions of deep space, where no galaxies cluster, that background light arrives just a little differently. The shape of space affects not just where light travels, but how long it takes to get there. And this tells us that the openness of space expands more than just distance. It expands time itself. It also gives us insight into the ultimate fate of the universe. If the universe keeps expanding, and galaxies drift ever farther apart, then over time, each region will become more like deep space. Less gravity, less light, less structure, and in that great emptiness, time will stretch even more. In the far, far future, when stars burn out, and black holes evaporate, and galaxies go dark, the universe will be mostly flat, not in shape, but in energy, and in that flatness, time may flow so freely that seconds stretch to infinity. This is speculative. We don't know if time can stretch forever, but if the trend continues, if gravity loosens its grip, then deep space may become the dominant clock of the cosmos, a place where seconds pass, not faster in perception, but with less resistance. A clean rhythm, unbent by weight. And if time flows fastest in the quietest corners of the universe, then the most silent places may be where the future happens first. There is a clock, moving silently through space, circling the Earth again and again, not ticking, not chiming, but pulsing, quietly, precisely, in the rhythm of atomic time. It's part of a satellite, orbiting high above your head, and it holds a secret, a confirmation, a quiet proof of something once doubted, once dismissed. Einstein said time bends. He said gravity slows it. He said motion warps it. And for a long time, these ideas lived only in equations, in the abstract curves of space-time. But this orbiting clock, this piece of machinery launched from Earth, turned the theory into measurement. It made time's flexibility real. In the 1970s, scientists placed an atomic clock aboard a rocket. They wanted to test Einstein's prediction that a clock in orbit, moving fast and far from Earth's gravity, would tick at a different rate than one on the ground. This was not a metaphor. This was not thought experiment. This was hardware. Metal, wiring, cesium atoms. A machine designed to count the pulses of time with incredible accuracy. They compared the orbiting clock to an identical one on Earth. They tracked both. They watched the seconds unfold, and they saw it. The drift, the difference. The orbiting clock was ahead. Not broken, not malfunctioning, just ticking in a different layer of time. And it matched Einstein's prediction to the smallest decimal. This was more than a test. It was a turning point. Because from that moment forward, we could no longer pretend that time was fixed. It had shape, and that shape could be measured. Since then, more clocks have gone up, better ones, more accurate. Each time, they confirm the same truth. Time on a satellite is not the same as time on Earth. And we have to account for it. GPS satellites, those quiet companions overhead, each carry atomic clocks. And those clocks drift ahead of Earthbound time by about 38 microseconds per day. That sounds small, but if we ignored it, GPS positions would drift by kilometers every day. Maps would fail, navigation would become useless. So every GPS satellite applies corrections, built-in equations that compensate for both special relativity, the speed of orbit, and general relativity, the weaker gravity up there. Without Einstein, your phone would be lost, your car wouldn't know where it was. Planes couldn't fly with precision, rockets couldn't reach their targets. We live in a world where relativistic time is not science fiction. It's infrastructure, this orbiting clock. And those that followed it proved that Einstein's view of time is not just elegant theory, it is the operating system of the modern world. And yet, there is still something humbling about it, because we do not feel the change in time. Standing on Earth, we do not sense that our seconds are slower than those in orbit. And in orbit, astronauts feel no great leap, no rush of time, yet the clocks record the truth, an invisible truth, a truth written in the shape of space. The orbiting clock shows us that time is not universal. It is local, personal, shaped by where you are and how fast you move. A second in space is not the same as a second on the ground, and that means time is not the ruler, but the ruled. Not fixed, but flexible. Einstein called this proper time, the time experienced by an object moving along a specific path through space-time. And every path has its own tempo. You and a satellite can both exist for the same number of proper seconds. But when compared, your clocks won't match. Because your paths are different, your gravity is different, your speed is different, and so your time is different. The orbiting clock doesn't lie. It just follows its path. And its path leads through a shallower gravity well and a faster speed. The two effects work in opposite directions. Gravity makes time tick faster in orbit, but speed makes it tick slower. And when both are combined, the result is a net gain. The clock in space runs ahead. We've measured this again and again, and every time the result agrees. So now, we live in a world where every satellite is a time traveler, not by years, not by drama, but by microseconds. And those microseconds matter. They accumulate. They guide planes, ships, phones, autonomous systems. They power the digital rhythms of modern life. And they all depend on the quiet drift of an orbiting clock. What makes this even more beautiful is the precision. The cesium atoms inside an atomic clock vibrate at a known frequency, 9,000, 92,000, 630, 70 cycles per second, and that vibration, that steady pulse, becomes the heartbeat of time. But that heartbeat is not immune to motion or gravity. In orbit, it beats just a little faster, and with that faster beat, we see space and time, not as abstract ideas, but as real, physical landscapes. The clock reveals the terrain, and the terrain is curved. You might think, is this really important? Is a difference of a few microseconds per day worth all this effort? And the answer is yes, because it shows us that reality is stranger than we thought, and more elegant. It means that clocks are not just tools, they are sensors, instruments for reading the shape of space-time. And when one clock orbits, it tells us where time is stretched, and where it is compressed. And this doesn't stop with Earth. If we send clocks to Mars, to Jupiter, to the outer solar system, they will tick differently again. And if we ever fly close to a black hole, the change will be dramatic. An orbiting clock becomes a probe, not of motion but of time's fabric. And each orbit writes a signature on that fabric. So when you look up and see a satellite crossing the night sky, know this: you are watching a clock that proves space and time are not what they seem. You are watching evidence that Einstein was right, and you are watching a part of our world that runs on curved time. Look up at the night sky. The moon hangs there, quiet, familiar, steady. Its light is soft, reflected from the sun, but its pull, its gravitational grip on the earth is anything but gentle. We see its power in the tides, in the shifting of oceans, in the slow breathing of the planet's waters. Twice a day, every coastline in the world moves, swells and retreats, not because of storms, but because of the moon. But what you don't see, what you don't feel, is something else the moon does. It stretches not just water, but time. The moon's gravity pulls on the earth, not only shaping its oceans, but tugging ever so slightly on the very fabric of space-time here on our planet. And because time is woven into space, the moon's influence on Earth includes time itself. It's subtle, you can't detect it with your senses. Your heartbeat won't change. Your breath won't stutter. But your seconds, those quiet, ticking units of your life, stretch and bend ever so slightly as the moon passes overhead. This isn't a metaphor, it's real physics. The moon's gravity alters the curvature of space-time on Earth, and that curvature shapes the flow of time. It's the same principle we use when talking about general relativity, mass curves, space-time, and time slows in stronger gravitational fields. So when the moon is directly overhead, its pull adds to Earth's gravity, changing the overall field ever so slightly, and that change, as small as it is, alters time. When the moon is high in the sky, a clock on the surface beneath it ticks just a tiny bit differently than when the moon is on the horizon. The difference is minuscule, far smaller than the time shifts caused by Earth's own mass, but with precise instruments. With atomic clocks sensitive to billionths of a second, we can detect it. And we do. This bending of time by the moon is part of a larger picture, a picture where time is not a constant, not an invisible metronome in the sky, but a living, changing dimension, shaped by all mass, no matter how distant. Even a body as seemingly distant as the moon can stretch time on Earth, and not just with its presence, but with its motion. The moon orbits us. It moves in an ellipse, changing its distance from Earth over time, sometimes closer, sometimes farther, and as it moves, its gravitational effect on Earth's space-time shifts, and time bends with it. The whole Earth, under the moon's influence, experiences a gentle rocking in time. This rocking is synchronized with the tides, with the moon's phases, with its journey across the sky. But there's more. The moon doesn't just cause time to change on Earth. It also slows Earth's rotation. This is tidal friction. The moon pulls on the oceans, and the oceans push back. This exchange of force acts like a brake on the Earth's spin. Our days are slowly getting longer, by about 1.7 milliseconds per century. Not because the Earth is tired, but because the moon is steadily draining its angular momentum. And with that slowing spin, the length of a second, as we define it by rotation, shifts too. We've had to add leap seconds to our clocks to keep Earth time in sync with atomic time. And the reason? The moon's pull on Earth. is changing not just the oceans, but our very sense of time. Imagine this: hundreds of millions of years ago, a day on Earth was only 22 hours long. The moon was closer, its pull stronger, the tides more intense. As it receded, the days lengthened, the moon's grip loosened, and time in the form of day and night stretched out. So the moon has been sculpting time on Earth for eons, and it continues to do so now. Not in dramatic ways, but in the quiet drift of a six, in the shape of days, in the rhythm of atomic clocks. It is a reminder that time, as we live it, is tied to the cosmos. Not just to gravity, but to movement, to dance, to orbits. The Earth and Moon are locked in a gravitational embrace. As the moon moves around us, and as we spin beneath it, time on our planet bends, stretches, slows. Even land rises and falls under the moon's pull, a phenomenon called earth tides. The solid ground shifts by centimeters, and when that ground rises, so does the local gravitational field. And with that change, even the pace of time adjusts. So when you walk along the beach at low tide, you are walking through a valley in time. And when high tide comes, you are standing beneath a bulge of space-time, lifted by the moon's invisible hand. Again, the effects are small, microscopic, but real. And with every orbit, the moon reshapes the flow of time on Earth, as if dragging its fingers through the river of seconds. And if the moon were to vanish, if it disappeared from the sky, the rhythm of time here would change. Our days would shorten, the tides would flatten, and the small fluctuations in Earth's time field would smooth out. But we would lose more than just tides. We would lose the mirror in the sky that shows us how motion and gravity sculpt not just the oceans but the clocks we build and the seconds we live. The moon is more than a satellite. It is a quiet timekeeper, and it reminds us that every moment we experience is part of a cosmic story. A story written not just in stars but in orbits, not just in math, but in motion. And in that motion, we find time always changing, always flowing, always shaped by the moon. Picture yourself floating above the Earth, not flying, not falling, but gently drifting inside a small silver capsule, circling the planet at over 27,000 kilometers per hour. This is the International Space Station. And here, everything is different. You are weightless. Your arms drift upward when you sleep. Your legs no longer press into the ground. Your body stretches, your spine decompresses, and your senses adjust to a world where up and down have no meaning. But there is something else changing. Something quieter than breath, quieter than muscle, quieter even than your thoughts. Your time is changing. Your seconds, those unseen measures of experience, are stretching just a little longer. Your heartbeat, steady and calm, moves through time differently here than it does on Earth. If someone on Earth and someone on the station started clocks at the exact same moment, something strange would unfold. The person on Earth, standing still on the surface, would age just a little faster than the person floating overhead. This is not science fiction. This is not theory. It is a real measured effect, predicted by Einstein and confirmed by the most sensitive instruments we have. Time ticks more slowly on the International Space Station. And that means, in a very real sense, your heart beats slower in orbit, not because the heart is weaker, but because the time around it is flowing at a different rate. Why does this happen? It all begins with two ingredients: gravity and speed. When you're in orbit, you are farther from Earth's center than you are on the surface, and farther from mass means weaker gravity, and weaker gravity means faster time. But you're also moving very fast, tens of thousands of kilometers per hour, and motion, according to special relativity, slows time down. These two effects, weaker gravity speeding up time and motion slowing it down, compete, and on the space station, the motion wins. Even though you're higher up, the speed of your orbit slows your time more than the reduced gravity speeds it up. The result? Your clock runs slower than one on the ground. Your seconds stretch, your heartbeat, your thoughts, your breaths. They unfold in a time frame that is slightly behind Earth's. It's not enough to feel. It's not enough to change your schedule. But it's there, and if you stayed in orbit long enough, then returned to Earth, you would find that everyone else had aged, just a little more than you had. This is called time dilation. It has been tested with atomic clocks flown on planes, launched on rockets, placed on mountaintops, and it always agrees. Time is not universal. It bends with speed and gravity. On the space station, astronauts experience this every day, without ever noticing. They float through a time field that is just a little different, and so do their heart. Every beat, every pulse of blood, every signal from the brain moves through this slightly stretched time. The change is incredibly small, a few milliseconds over 6 months, but it accumulates, and it's real. The human body, though unaware, is still subject to the laws of space-time, and because the space station is in constant motion circling the Earth every 90 minutes, its astronauts live in a rhythm that never touches the surface. They rise above the gravity well, into a thinner region of space-time, and the heart, pumping calmly in microgravity, beats to that rhythm. But the story doesn't end there. The space station also affects the biology of the heart, not just through time dilation, but through the experience of microgravity itself. In orbit, blood shifts. It moves from the legs to the chest. The heart, sensing extra fluid, adjusts its output. It doesn't have to pump as hard to move blood around. Over time, the heart muscle can weaken. It shrinks slightly. It becomes more efficient, but also less robust. And with less effort required, the heart rate drops. This is a biological adaptation, and when combined with relativistic effects, it paints a curious picture. Your heart, in space, beats slower, not only because time has stretched, but because the environment has changed its needs. You are both floating in a different flow of time, and living in a body adapting to that flow. The difference is tiny, but in science, tiny is profound. It tells us that the body and time are more connected than we often realize. That time is not just a background for biological processes. It is an active participant. The rhythms of life play out on a stage that bends and flexes with speed and gravity. On Earth, your heart beats to a tempo shaped by one kind of gravity. In orbit, it finds a new tempo. And this knowledge shapes the way we plan for space travel. Long-term missions to Mars, to the Moon, to deep space require us to understand how time will pass differently. Not in dramatic leaps, but in quiet divergences that add up. 2 astronauts, leaving Earth together, can return with slightly different ages than those who stayed behind. Their cells, their organs, their clocks, all slightly out of sync with the planet they left. And the longer they stay in orbit, the more the difference grows. One day, we may have to think carefully about synchronization, about how time, experienced in orbit, affects biology, memory, coordination. But for now, what we know is this. Your heart in space is part of a body living in stretched time. Its beats, its pauses, its quiet persistence. They are all woven into a stream of seconds that moves just a little more slowly than it does on Earth. And yet, that heart remains steady, constant, anchored beats. For a body suspended above a spinning world, moving fast, living gently, aging just a touch behind. Imagine you're taking a journey. You step onto a train, feel it begin to move beneath you, and watch the landscape glide past the window. The motion is smooth, rhythmic. Your body adjusts easily to the subtle sway of the rails. Your phone in your pocket quietly ticks away, counting the seconds of your trip. Now picture a different journey. You walk through an airport, find your seat on an airplane, and rise into the sky. The earth drops away beneath you, and the clouds become your ground. Again, your phone ticks on, each second seemingly identical to the last. But something subtle is happening, something your body can't detect. Even your phone doesn't notice. Yet time, measured down to its smallest pulses, is not flowing equally in both journeys. The clock on the plane is ticking at a slightly different rate than the clock on the train. This is not imagination. It is not an illusion. It is measurable. And it has been measured with atomic clocks, precise enough to detect changes of billionths of a second. Why does this happen? Because time, as described by Einstein's theory of relativity, depends on both motion and gravity. Neither journey is immune to these effects, and even at human speeds, even across the brief span of a domestic flight or a train ride, time shifts. Just a little. The train travels quickly, but it stays close to Earth's surface. Its speed is moderate, and its position in Earth's gravity remains fairly constant. The airplane, however, moves faster, and it flies higher, farther from Earth's center of mass. That difference matters. The higher you go, the weaker the pull of gravity. And in weaker gravity, time flows faster. This is gravitational time dilation. But speed also changes time, and speed slows it down. This is time dilation due to motion. Special relativity at work. On the train, you're moving slower than the plane, so the speed-based time dilation is smaller, but you're closer to Earth's mass, which means gravitational time dilation is stronger. On the plane, your speed causes a greater slowing of time, but your altitude causes time to speed up. The result is a delicate balance, a push and pull between motion and gravity. In most typical passenger flights, the gravitational effect is slightly stronger than the effect of speed, so your clock on the airplane actually ticks a little faster than a clock on the ground. Not slower, despite your high speed, but compared to someone on a fast-moving train, the difference is tiny. The train's clock ticks a little slower because of gravity. It is deeper in Earth's gravitational field, but the motion is also less intense. In both cases, the changes are unimaginably small, fractions of a microsecond. But when you place ultra-precise atomic clocks on board airplanes and synchronize them with ground-based clocks, you can watch this difference unfold. In the famous Hoffele-Keating experiment in 1971, 2 atomic clocks were flown around the world, one eastward, one westward. They were compared to a stationary clock on Earth, and when they returned, the clocks no longer matched. The difference was exactly what Einstein's equations predicted. The motion of the plane slowed the eastward clock. The direction of travel, combined with Earth's own rotation, added to the total speed, and the time stretched. The westward clock, traveling against the spin of the Earth, had a lower net velocity, and its time stretched less. When compared to the ground clock, both flying clocks were out of sync. Not because they were wrong, but because they had followed different paths through space-time. And from this experiment, we learned something profound. Every journey, whether by train, plane, or rocket, carves a unique trail through time. And each trail writes a different signature on the clock that travels it. It means that when you fly, you don't just move through space, you move through a different time. Not a different time zone, a different tempo of time. You leave Earth's surface, where gravity is stronger, and rise into the thinner atmosphere, where gravity weakens and motion increases. And those two effects change the rhythm of your seconds. Your heartbeat is the same, your breath unchanged, but the clock in your wristwatch, if it were precise enough, would slowly diverge from the one you left on your desk. We don't build our lives on such subtle differences, but physics does, and satellites do. GPS systems, which rely on high-speed satellites in orbit, must constantly correct for both kinds of time dilation, gravitational and motion-based. Without these corrections, navigation would be wildly inaccurate, and that's why understanding the difference between clocks on planes and clocks on trains is more than trivia. It's the foundation for every modern positioning system we use. It's also a reminder that time is not a backdrop. It's a participant. It flexes with speed. It bends with gravity. And it flows differently, depending on the journey you take. That a passenger riding the subway, moving quickly underground, experiences a slightly different slice of time than someone relaxing in a park above. The effect is invisible, but it's real. The speed of the train slows time by a hair. The depth, underground, pulls time a little tighter. The result is a clock that ticks just a little more slowly than a clock resting on the Earth's surface. And for an airplane passenger, the experience reverses. Higher altitude, less gravity, time moves faster. Higher speed, more motion, time moves slower. But because the gravitational shift wins out, you age slightly more than your friends back on the ground. It's a curious reversal of what we usually expect. We think of speed as the dominant force in time dilation, but gravity often has a stronger say. And this is why two people taking different routes through the sky and the rails can arrive at the same destination, with clocks that no longer agree, even if only by billionths of a second. It's not enough to note, not enough to measure with ordinary tools. But the universe keeps track, and physics never forgets. You may be wondering, if this happens with trains and planes, what about walking, running, biking? Yes, even there the effect exists. It is smaller still, but it is real. When you run, your heart speeds up, your breath grows heavier, but your time slows down. A few atoms worth, but physics counts it. Every motion, every shift in elevation, every gravitational curve adds to the complex choreography of time. And so we return to the idea that time is not fixed. It is not one clock for all. It is a tapestry, woven from gravity and speed, stitched with the threads of every journey we take. Picture a train station. Quiet, dignified, steady, a place of departure and arrival, a place where time is measured by the rhythm of footsteps, the chime of a departing bell, and the steady pulse of trains sliding along steel rails. In the late 1800s, one such station stood in Bern, Switzerland, a city of clocks, trams, cobblestone streets, and precision. A young man walked those streets every day. Not a physicist, not yet, a patent clerk. Curious, restless, thinking about time in a way no one else had. His name was Albert Einstein. And the trains that moved through that quiet station would eventually move through his mind and rewrite the laws of the universe. He began with a question, a simple one, but one that cut deeper than most had dared to ask. What does it mean for two events to happen at the same time? We say it so easily. The clock strikes 12. The train departs. But how do we know those things are simultaneous? What if two clocks, one on the platform, one on the train, disagree? What if motion changes the experience of time? Einstein imagined standing on the train platform, watching a lightning bolt strike both ends of a moving train. To the person on the platform, both flashes arrive at once. They seem simultaneous, but to a person on the train, moving toward one flash and away from the other, the light from each bolt arrives at a different moment. Same event, different frame of reference, different experience of time. So, simultaneity, the very idea that two events can happen at the same time, falls apart when we introduce motion. From this small idea, an entire theory was born. Special relativity. Einstein's insight came not in a laboratory, not with equipment, but in the humble act of watching trains and wondering how light behaves for different observers. The train became a metaphor, a thought experiment, a vessel not only for people, but for ideas. He imagined riding alongside a beam of light. He imagined observers moving at different speeds. He imagined clocks synchronized by pulses of light, then broken apart by motion. And from those imaginings, he built a new view of reality, one in which time is not absolute, but flexible, personal, relative. And it all began with the quiet, orderly space of a train station. We often think of revolutions as noisy things, but the revolution of physics that Einstein began was almost silent. A young man watching trains, questioning clocks, and asking what others had assumed. He realized that if you move fast enough, your seconds stretch. Your measurements of space contract. Your sense of now becomes yours alone. And that's when time stopped being universal. The clock on the train, moving swiftly along the tracks, ticks, differently than the clock on the platform. And this is not theory anymore. We have measured it. Modern physics has confirmed that motion stretches time, and the same station in Bern that once hosted Einstein's curiosity now bears a plaque commemorating the imagination that passed through its halls. Einstein's time in the patent office was spent reviewing inventions, but his mental experiments, his real work, was playing out in the form of trains and beams of light. And the simplicity of it is stunning. He did not need super collider. He needed a question, a frame of reference, and the patience to think deeply. He understood that what we call time is not a ticking in the sky, but a relationship between events, between observers, between clocks. And that realization changed everything today. We still use his thought experiments. They are taught in classrooms, used in textbooks, guiding new generations into the mysteries of physics, the train and the platform, the moving clock and the still one, the flashes of lightning. They are now tools of explanation. But once, they were sparks in one man's imagination, and they lit a fire that still burns through science today. Even more profound is what followed. Special relativity led to general relativity, a theory that includes gravity. And in that theory, Einstein showed that mass bends space-time, and that time slows in gravitational fields. Now, we can understand why clocks on satellites tick differently than those on Earth, why your GPS system needs corrections, why time is not the same everywhere, but it all goes back to that quiet train station. A place where questions began. A place where stillness and motion created contrast. Because without contrast, you cannot see the bend. Einstein used trains to reveal that time and space are not fixed backgrounds, but active, dynamic quantities. And in doing so, he reshaped the universe. Even now, physicists return to the train. They use its motion to explain why simultaneity fails, why two people moving relative to each other experience different timelines. They use it to show how causality must be preserved in a world where time bends. They use it to explore paradoxes, like the twin scenario, where one sibling travels at high speed and returns younger, all because Einstein, watching the trains glide through Bern, refused to take time for granted. He saw that something we think of as obvious might not be so. And in that doubt, he discovered depth. It's strange, perhaps, that something so profound began with something so ordinary. A station, a schedule, a pair of tracks, stretching into the distance. But that's how insight often arrives. Not through drama, but through quiet, reconsideration. So now, when you sit in a station watching the world move, remember what Einstein saw. Not just trains, but the invisible geometry of time itself. Not just departures, but divergences in experience. Not just a platform, but a frame of reference. And maybe, if you look closely, you'll see what he saw that time is not an arrow, but a field. Not a rule, but a relationship. Not a background, but a participant. And it all began with one man, one clock, and one train, pulling gently out of the station. Beneath your feet, beneath the dusty plains and ancient craters, beneath the silence of a world without wind or water, time passes in a different rhythm. This is the moon. Not the glowing crescent in the sky, but the world beneath that light, solid, grey, barren, and beneath its surface, in the layers of rock and regolith, in the slow cooling of ancient lava flows, something subtle unfolds. Time, as measured by the ticking of a perfect atomic clock, moves just a little differently here than it does on Earth. This difference is not visible. It doesn't echo. It doesn't shimmer in the dust. But it is real, and it is written in the geometry of gravity itself. On Earth, your body feels weight. Your bones resist a constant pull. Your heartbeat adapts to pressure. Your sense of time feels consistent, even though it's shaped by the mass beneath you. On the moon, that pull is weaker. Gravity is only about 1/6 as strong, and where gravity is weaker, time stretches, seconds are slightly longer. Not in feeling, not in rhythm, but in measurement. A clock on the moon ticks faster than a clock on Earth, and deeper beneath the surface of the moon, gravity's pull grows ever so slightly, not because the moon becomes heavier, but because you are closer to its center of mass. And so, time adjusts once more. A clock just beneath the lunar surface ticks more slowly than one on the surface. It is a gentle shift, fractions of a microsecond, but real. And if you built a base there, if you placed a lab underground and synchronized clocks between the surface and the subsurface, you would begin to see them drift apart. Not broken, not wrong, just different. This is the truth of relativistic time. It bends with position. It warps with gravity. And every change in elevation is a change in experience. The moon has no atmosphere, no tides, no oceans to swell and retreat. But it does have depth, and with depth comes gravity's gradient, and with that, a shifting of time. In the vacuum of space, where gravity weakens, time opens. On Earth, deep in a mine or under the ocean, time tightens. And on the moon, though gravity is weaker than Earth's, the same rule applies. Deeper means slower. The difference is so small, you'd need an atomic clock, precise to 10^-20 seconds to measure it. But with such tools, we have done just that. On Earth, we've placed clocks on tabletops, raised one a centimeter higher than the other, and seen them tick at different rates. So if a difference of 1 centimeter can bend time, then imagine what happens tens of meters beneath the lunar surface. Imagine a tunnel, carved beneath the regolith. Perhaps a base built into lava tubes, sheltered from radiation and meteorites. A place of quiet science. In that base, your heartbeat would still be yours. Your thoughts, unchained. But the seconds around you would stretch differently than those just above. And if someone stood on the surface, and you stood beneath, and both of you watched identical clocks, the readings would eventually diverge, and the moon, so small, so quiet, would once again show that time is never absolute. You might ask, why does this matter? Why care about a difference of billionths of a second? Because it tells us that time is local, intimate, bound to position. And as we prepare to return to the moon, to build, to stay, to live there, we must understand time, not just in theory, but in practice. Navigation systems on the moon will require precision. Clocks must be synchronized, not just in orbit, but on the surface and beneath it, because even small drifts can break coordination. Imagine autonomous rovers exploring caves, labs performing experiments on lunar geology, data relayed between modules, between levels. Each clock, each node, each depth must account for time's subtle bending, and it begins with understanding how gravity affects time beneath the surface of the moon, in the quiet, in the rock, in the stillness. And perhaps there's something more poetic here. On Earth, we live within a thick atmosphere. We feel weather, storms, sound, but on the moon, all is still. There is no noise, no water, no erosion, just the slow shift of dust and time. And even time does not pass equally everywhere. This is one of the great revelations of general relativity. Mass bends space, and time flows through that space at different rates. So when you dig into a world, you dig into its time. The tunnel is not just a space, but a temporal descent. And the moon, though it has no seas, has tides of its own, tides of time. On the surface, time is lighter. Deeper down, it is heavier. And every clock, every second, every flicker of measurement records that difference. As we prepare to live beyond Earth, to build on new worlds, we must bring time with us. But we cannot assume it behaves the same, because it doesn't. And the moon, silent and still, teaches us that, beneath its surface, in the cold rock, in the gravity that holds it together, time tells a different story, 1 second at a time. Imagine two worlds circling the same sun, both covered in dust, shaped by ancient forces, but each walking through time in its own way. Venus, wrapped in thick clouds, pressing down with an atmosphere heavier than Earth's oceans. And Mars, red and dry. Its sky thin. Its grip gentle, barely holding on to the faint traces of its past. Both planets move through space, but not through time equally. Because time, as strange as it may seem, does not pass at the same rate on every world. It stretches, bends and flows at different speeds, depending on how deep a planet sits in the well of gravity. This is not science fiction. This is relativity, and the Sun, massive and dominant, sets the tempo for each planet's clock. Venus is closer, its orbit tight, its days long. But its proximity to the Sun means it feels more of the Sun's pull, and where gravity is stronger, time slows. On the surface of Venus, a perfect atomic clock would tick just a little more slowly than it would on Mars, not by much, but enough to matter if you could measure precisely enough. Now think of Mars, farther from the Sun, smaller than Earth, lighter, its gravity is weaker, and farther from the Sun, it experiences a gentler curvature of space-time. A clock on Mars would tick a little faster than one on Earth, and faster still than one on Venus. And if you placed 3 clocks, one on Venus, one on Earth, and one on Mars and kept them synchronized, they would slowly drift apart. The Venusian clock would fall behind, the Martian clock would leap ahead, and Earth's would sit in the middle. This difference is invisible. You wouldn't feel it in your heartbeat. Your breath wouldn't change. Your senses would notice nothing. But physics would. And if you were to live on Venus or Mars, even for a short time, and then return to Earth, you would discover that others had aged ever so slightly differently. Not from motion, but from position. This is gravitational time dilation. Einstein showed us that the deeper you are in a gravity well, the slower your time passes. And Venus, tucked close to the Sun, sinks deeper into that well. It also has gravity stronger than Mars, adding another layer of dilation. On Mars, time flows more freely. Seconds stretch, just a little longer. And over months or years, those small differences begin to add up. But there's more to consider. Each planet also spins. Each planet moves. Mars rotates quickly. A day on Mars is roughly 24 hours and 37 minutes. Venus spins slowly. So slowly, in fact, that a single day on Venus is longer than its entire year. But for time dilation, what matters most is gravitational depth and orbital motion. And in those aspects, Venus is the world where time clings tighter, where seconds resist, and clocks hesitate ever so slightly. Now imagine a future where humans live on both planets, scientists on Mars, engineers on Venus, all working together, sharing data, sending signals across millions of kilometers. Their clocks must be aligned. Their systems must agree. But nature doesn't make that easy, because even if every machine is perfect, the passage of time itself is not. Synchronization requires correction. Software must account for each world's position, each world's motion, and each world's mass. And if you were to walk on Venus, through dense air and under burning skies, you would be living a life that moves, just a fraction of a second slower than the same life lived on Mars. A twin, born with you, raised beside you, but sent to the red planet, would come back slightly older than you, though by an amount so small it could be missed by eye, but never by physics. It's a strange thing to consider that the universe does not agree on the pace of a second. We think of time as constant, a universal metronome, but it isn't. It is a fabric, and that fabric stretches differently over each world. The Sun tugs on each planet with a different strength, and that tug shapes the passage of time. On Venus, closer, denser, seconds shrink. On Mars, distant, lighter, seconds grow. And the story becomes more complicated when we add spacecraft, satellites, orbiting probes. Each one moves at high speed. Each one changes position constantly, and each one carries a clock that experiences a slightly different flow of time. When orbiters relay information from Mars to Earth, or from Venus to Earth, their signals must account for this, or else coordinates drift. Landings miss, data desynchronizes. So even though the difference is small, The implications are not. Our exploration of other planets depends on our understanding of time as a flexible, local phenomena. And one day, when people live on both Venus and Mars, time will no longer be just Earth's domain. Calendars will shift, days will stretch or compress, and timekeeping will be an interplanetary art. We may someday define time, not just by Earth's orbit, but by a universal reference, a cosmic clock, somewhere beyond the planets, steady and impartial. But even then, local corrections will remain, because time, at its core, is tied to gravity, and gravity changes with every step you take across the solar system. Imagine drifting just above the swirling clouds of Jupiter, the largest planet in the solar system. Its storms are vast, its bands stretch like rivers of color, and its gravity holds dozens of moons in silent orbit somewhere among them. 4 giants circle steadily: Io, Europa, Ganymede, and Callisto. These are the Galilean moons named for the man who first observed them through a modest telescope 400 years ago. They glide in quiet resonance, each one locked in rhythm, suspended in the gravity of a world so massive that even light bends gently as it passes near. But beneath the stillness, something subtle is unfolding. On every one of Jupiter's moons, time is moving a little more slowly than it does on Earth. This is not a poetic feeling. It's a physical reality, an effect of gravity, a side effect of being tethered to one of the heaviest objects in the solar system. Jupiter's gravity is immense, over 2.5 times stronger than Earth's, and with great gravity comes a deeper well in space-time. And in that deeper well, time flows more slowly. This is called gravitational time dilation, a prediction of general relativity, one that has been measured, confirmed, and woven into the very fabric of modern physics. If you were to place an atomic clock on Ganymede and another identical clock on Earth, and let them tick side by side, they would not agree for long. The clock on Ganymede, though it experiences lower surface gravity than Earth, is caught in Jupiter's powerful gravitational field, and it ticks just a little more slowly than the one back home. And the closer the moon orbits to Jupiter, the stronger the effect. Io, the innermost of the Galilean moons, suffers the strongest time dilation. Its orbit carries it deep into the gravity well. Its seconds stretch, even if imperceptibly. On Europa, where oceans may lie beneath ice, time still moves more slowly than it does on Earth. On Ganymede, the largest moon in the solar system, bigger than Mercury, with its own magnetic field and layered structure, time remains bent under Jupiter's influence. And Callisto, the farthest of the 4, dances on the edge, experiencing slightly less dilation, but still enough to matter. Each moon becomes a clock, not just of orbital cycles, but of time itself, and every journey through Jupiter's domain becomes a slow march through seconds that do not pass as quickly as they do farther from the giant planet. You would not notice it in your breath, your pulse, or your sleep, but the physics would know. And if you stayed long enough, and then returned to Earth, you would discover that the people you left behind had aged just a little more than you. Because in the curved space-time around Jupiter, your experience of time was slightly delayed. It's a strange truth, but one that becomes even more curious when we look at how these moons behave. They are constantly flexed by Jupiter's pull, especially Io, which is the most volcanically active body in the solar system. This constant tidal stretching heats the interior, reshapes the surface, and drives a unique kind of geology. And through it all, the slow drag of time continues. In the deep infrared, in the signals sent from passing spacecraft, we measure time precisely, and every orbit, every signal, tells us more about the bending of time around a planet that is over 300 times more massive than Earth. On these moons, the seconds may be slower, but the science unfolds quickly. Galileo first saw them in 1610, a moment that shook the world, because for the first time, we had proof that not everything in the heavens orbited the Earth. Now we understand more, that even time does not behave the same across all orbits, and as we prepare to send missions to Europa, to Ganymede, to the ice and rock that orbit Jupiter, we must account for these differences in time. Our clocks must correct for it. Our communication systems must adjust, and our models must predict how time behaves under the weight of such mass. Even the GPS satellites around Earth must correct for both special and general relativity. If they didn't, navigation would fail. So when we send orbiters and landers to Jupiter's moons, we face a similar challenge, not because time dilation is huge, but because it matters at the level of precision needed for exploration. And one day, if humans walk on Europa, or build laboratories on Ganymede, their clocks will tick just a little behind. Their days will stretch imperceptibly, and over months, years, those small differences will add up. They will live in a different time flow, not because of culture or biology, but because of where they stand in the curved geometry of space-time. And that thought reminds us how fragile and local our experience of time really is. The tick of your watch, the rhythm of your breath, the pulse in your temple, they are all grounded in gravity. On Jupiter's moons, gravity holds the rhythm tighter, and the seconds slip just a little slower. This difference is not just a curiosity, it is part of the architecture of the universe. And when we understand it, we open the door to deeper truths about how time behaves. Not just near stars, but in every corner of space, where mass distorts the stage, on which everything unfolds. Imagine something small enough to hold in your hand, but heavier than all the mountains on Earth combined. A sphere no wider than a city, but dense enough to bend starlight around it. This is a neutron star. What remains when a massive star dies, collapsing under its own gravity, compressing atoms so tightly that electrons and protons fuse into neutrons? What is left is a core of pure density, a spinning, pulsing relic of unimaginable pressure and gravity. But it does more than just bend light, it bends time. And near its surface, seconds stretch longer than anywhere else outside a black hole. This is not a trick of perception, not a theory. It is real. And if you could place a clock on the crust of a neutron star, a clock capable of surviving the crushing weight and devastating radiation, that clock would tick dramatically slower than a matching clock far away in open space. You would not hear the ticking. You would not see the hands turn, but physics would measure the difference. And what you would find is that near a neutron star, time nearly stands still. This is the timeless shadow. Not silence, not stillness, but a slow dragging of time itself, pulled taut by gravity too strong for matter to resist. Imagine a beam of light, climbing away from the surface of a neutron star. It struggles, loses energy. Its frequency stretches into red. This is gravitational redshift, and it tells us how deeply time is bent in that place. Astronomers see it from afar, in the light that escapes, in the pulsars that spin, flickering like cosmic lighthouses. Some spin hundreds of times per second, and yet, even their precision, even their rhythm, is not immune to time's distortion, because their surface lives near the edge of where space-time folds too tightly to escape. They are not black holes, but they are close. And just as a clock near a black hole slows, so too does a clock near a neutron star. The deeper you go into gravity, the slower time flows. This is a core truth of general relativity. Mass curves space, and time flows through that curve. So near a neutron star, you are deeper in the well, farther from flatness, closer to the tipping point. And there, seconds stretch, minutes elongate, and the rhythm of reality slows. If you were to orbit just above the surface, safely beyond the crushing crust, and then return to Earth, you would find that more time has passed here than for you. You would be younger, by seconds, by hours, depending on how close you ventured and how long you stayed. This is time dilation at its most extreme, short of a black hole, and it means that the universe does not share a single tempo. Each star, each mass, each depth in gravity plays its own rhythm. On Earth, we live in a gentle well, deep enough to hold us, but not enough to pull on time too tightly. But neutron stars are a different world entirely. Their crusts are solid neutron matter. Their centers may hold exotic particles that no lab on Earth can replicate. Their mass, often twice that of our sun, is squeezed into a ball no more than 20 kilometers across. And in that compression, they carve a deep valley in space-time, deep enough that light itself hesitates, deep enough that time slows to a crawl, and yet they shine. They pulse. They dance across the sky in radio waves and X-rays, in the slight motions of stars tugged into orbit. Some are born in supernovae, blazing out with light and debris. Others hide in binaries, feeding on companions, spinning faster, growing stronger, and in their shadow, the seconds thin. You might think of it like a lens. The distortion not of vision, but of tempo. What seems a moment from afar might feel eternal up close, and what seems eternal up close might be only a breath from far away. This is the strange duality that mass brings to time. The more mass, the more gravity. The more gravity, the more curvature, and the more curvature, the slower the time. Near a neutron star, the equations bend hard, and if we had the tools to visit that shadow, to hover near its crust, to study the particles just above, we would feel time stretch around us. Communication would slow, or so. Measurements would shift, and signals would arrive, not when expected, but always a little late, because the universe would not agree on the pacing of the moment. Even now, we send telescopes to track them. We watch the flashes, count the pulses, measure the delays, and each delay tells us about the gravity. Each shift tells us about the mass. Each flicker tells us about time. It's why pulsars rotating neutron stars are some of the most precise clocks in the cosmos, and also the most distorted. Their internal time runs slower than the vacuum around them. Yet from Earth, they appear precise, because the distortions are consistent, and so we can trust them, even as we know they lie at the edge of time itself. The timeless shadow behind a neutron star is not darkness, it is not silence, it is the strange quiet of time dragging its feet. And the closer you go, the more you feel the pull, until seconds become longer than you remembered, until moments pass without movement, until time no longer feels like yours at all. And beyond that edge, if mass crosses a threshold, time halts completely, not for you, but for those watching from outside. That's the domain of the black hole, but the neutron star sits just before that threshold, a last stop before the drop. And in that place, where time still flows, but just barely, the universe teaches us how fragile and local our seconds really are. So as we listen to the pulses of the sky, counting the steady rhythm of neutron stars, we are not just listening to distant orb, we are listening to the stretched echoes of time itself, as it tries to climb out from gravity's grip. At the farthest edge of what we can see, there is a quiet fading, not darkness, not emptiness, but distance, so great that even light, traveling for over 13 billion years, arrives dim and stretched. This is the cosmic horizon, the limit of visibility, the edge of the observable universe, a boundary not of matter, but of time, because to look far away is to look far back. And the farther you look, the younger the universe appears. Galaxies, still forming, light, still red shifting, the early structures of space-time, barely set. This is not the edge of everything, only the edge of what we can ever receive. Beyond it, the universe may continue forever, but the light from those regions has not yet had time to reach us, and may never, because space itself is expanding. Not like things moving through space, but space growing beneath them. And, where expansion outpaces light, signals cannot cross. So beyond the horizon, communication is broken, not by distance, but by time itself. And at that edge, time behaves strangely, not because it stops, but because it stretches, because it thins, because it separates observers who will never again be able to compare clocks. If you stood near that edge, on a galaxy drifting close to the observable limit, your seconds would feel normal. Your heartbeat would tick steadily. Your days would pass like always. But to us, watching from across the cosmos, your time would seem frozen, slowed by motion, distorted by redshift, flattened by expansion. This is the cosmic time warp, not caused by mass, like around a planet or a star, but caused by motion through expanding space. And the edge of the universe is not a place in space, it is a place in time, a surface of last interaction. The cosmic microwave background, a faint glow from when the universe was just 80,000 years old, marks one such edge. A time when atoms first formed, when light could travel freely, when the universe became transparent. Beyond that, there was no vision, only scattering plasma, opaque and hot. But beyond even that, beyond what light reveals, the geometry of time continues, and it leads us to questions no telescope can answer. How fast is time flowing on the outermost fringe? What does a clock measure when it rides the expansion of space? What happens when galaxies disappear beyond reach? Because they are disappearing, slowly, inevitably, drawn by dark energy, into a future where they will no longer be visible. Each day, a few more galaxies slip past the horizon, not because they vanish, but because their light can no longer bridge the growing gap. In 1 trillion years, an observer in our galaxy may see nothing but darkness. The universe will still be there, but unreachable, uncountable, silent, and the time those distant places experience will be forever cut off from any point of comparison. In a way, they will have their own time. Local, sealed, unshared, and so will we. This is the strange consequence of an accelerating cosmos, that time, once thought universal, is fragmenting. Each galaxy, each cluster, each region of space is becoming its own island of causality, its own pocket of time, not because of choice, but because of the laws of expansion. And the edge of the universe is not a single line. It is different for every observer. From your eyes, the horizon is a sphere, roughly 46 billion light-years away in every direction, and from another galaxy, the same is true, but different. Their horizon, their edge, their time, and no two agree. This tells us something profound. That time itself is not just shaped by mass, but by distance, by movement, by expansion, and at the edge, time becomes more a suggestion than a shared experience. Even if we could travel fast, even if we had the power to cross galaxies, the distances grow too quickly. Light cannot keep up, and with it, the communication fails. This isn't just theory, it's baked into the equations of cosmology, into the structure of de Sitter space, into the strange properties of dark energy, which pushes galaxies apart faster than gravity can bind them. And what lies beyond? We do not know. Perhaps more galaxies, more stars, more time. Or perhaps something different, a region forever inaccessible, with different constants, different outcomes. We will never see it, because light will never come from there. Our universe, as large as it seems, is finite in what we can know, and that boundary, that quiet, distant limit, is set, not by walls, but by time. And so we live in a bubble of history, watching light from the past, moving into a future that becomes more alone. But even in that solitude, there is wonder, because to stand on the edge of time is to realize just how far light can go, how long memory can last, how precious every second is, when you know not all seconds are equal. And as expansion continues, and time continues to stretch, we remain connected to a universe that grows, not just in space, but in time's complexity. Each moment we observe is a layer of that tapestry, and every edge we approach reminds us that the story of time is not yet done.